Haloalkane details.
1 second.
Matchmakers co-host.
Do you want to open your half screen, the paper?
I don't know how to.
Go on.
Good morning, everyone, and welcome to the ACE Medics A-Level Chemistry January session, where we'll be looking at haloalkanes and reaction mechanisms. So thank you all for joining me on a Sunday morning. I know a lot of you guys were here yesterday as well during the biology session with us. But for those of you that are new and this is your first session with us, a really warm welcome to you guys. I'm Roshni, and I'm currently a doctor working in London, and I will be teaching today's session. I know you guys have had like weeks long classes of online sessions, so thank you all for joining me today. We will try and make this as fun and as useful as possible. So today's topic, last session we looked at alcohols. Today we're going to be looking at haloalkanes, and basically we're going to be talking about how to name them, because I know that can be a little bit challenging. The physical properties of haloalkanes, including the boiling point and reactivity, its chemical properties as well, so in particular reactions with silver nitrate. And we'll also be talking about reaction mechanisms, the main one being nucleophilic substitution. And then finally, we'll look at organohalogen compounds in the environment and the ozone layer, which is quite an important topic. So haloalkanes is one of my favorite branches of organic chemistry, and it is very interesting and complex, but nevertheless, we will take it step by step. So what is today going to look like? We will be taking a short 5 to 10 minute break every 45 minutes or so. So we'll start off this morning talking about haloalkanes, an overview and how to name them. We'll then go for a short break, and then we'll be talking about the actual reactions of haloalkanes. And then we'll be going for lunch from 12 to 1. And in the afternoon, we'll be doing the reaction mechanisms and talking about compounds in the environment. We'll be doing exam questions at the end, but there are also exam questions throughout the session, which are based on the question packs that you guys were given. So if you've done them, that's great. You can just refer back to them. But if you haven't, don't worry, we'll go through them together. Okay, so if at any point you've got any questions or you don't understand what I'm talking about, please just ask my colleague, Ask Ace, who is readily there sitting to answer your questions. You can also direct them to me as well. We will be doing lots of Kahoot quizzes today, and the way that these quizzes work is if you come first in all of the quizzes, you can come for free for the next session. So do get your hands ready on your keypad. And we have got lots of top tips as well. So whenever you see this light bulb sign, this is basically a take-home message and something that you should remember for the session. Okay, so if you guys don't have any questions or you're all okay, we're going to go straight into it. So we're talking today about haloalkanes. Okay, so we already know that alkanes are compounds which have got carbon and hydrogen. They are made up of single bonds. Okay. In particular, we're talking about haloalkanes. So that is the group 7 compounds. So those are our halogens. So this is, as I'm sure you know, a periodic table, and this is group 7 over here. So in organic chemistry, carbon compounds can be formed with a wide variety of different elements, but in particular, they form compounds with group 7. And these are very useful in the industry and for lots of products that we use in daily life. Okay, so the ones that we commonly talk about are usually chlorine, bromine, and iodine. Because of the significant differences in reactivity, we don't usually talk about fluorine or AT, which is a compound that's never actually been seen because it's highly reactive. So we usually just talk about chlorine, bromine, and iodine. And so normally you're used to just seeing chlorine like so, but when we name them with haloalkanes, the naming is slightly different. So I'll just show you guys how we do that. So as I said, haloalkanes are compounds containing carbon, hydrogen, and at least one halogen. Okay, that is what defines a haloalkane. Now, when we have to name our haloalkanes, it's very similar to how we named basic compounds in the last session, but you essentially add a prefix, which is the bit in the beginning, that comes first, to the name of the longest chain to basically identify what is the halogen. So for example, if it's fluorine, it would be fluoro. If it's chlorine, it would be chloro. And if it's bromine, it would be bromo. And if it's iodine, it would be iodo. So it's fairly straightforward, but the thing that you need to remember is that this comes at the front of the compound, okay? So let's say, for example, I've got a compound like so. Okay, so guys, just quickly jot down in the chat, what do you guys think this compound is called? Great, so a few of you have put some answers down and you've all said chloroethane. That's great. So this is a very simple compound. We know that it's ethane because there are 2 carbons, and we know that it's not ethene or anything else because there are single bonds only. So this is an alkane. It must be ethane, and we always put the halogen group at the front. Okay, this is the prefix. So you can't be writing like ethane 1,2-chloro, anything like that. The chloro has to come at the front. Okay, great. So let's just try, now that we've seen a really basic example, I want you guys to have a go at naming this one. So you can vote your answers in the poll. Excellent. So pretty much all of you guys have got the correct answer. So the way we do this is that, remember, we want to try and minimize the numbers and make the chain length as short as possible. So I'm going to identify where are my functional groups. So I've got a functional group here, which is my chlorine, and I've got another group here, which is my methyl group. So I want to then identify the longest chain. So I can see that there is 1, 2, 3, 4. Okay, therefore my the end bit will be butane. Then I look at my functional groups, so I can see that there is a chloro at 2, so I know it will be 2 chloro. Okay, and when you've got a number and a word, you put a dash in between. So I've got 2 chloro, and then also on group 2, I've got a methyl. So this will be 2 chloro, 2 methyl butane. Okay, so that is that one. So that is 2 chloro, 2 methyl butane. Well done. Okay, so let's have a go at another one, guys. Okay, fantastic. Well done, guys. So this one is a little bit more straightforward. So again, you want to just see, okay, so I've got my functional group here, and then I want to identify the longest carbon chain. This is carbon 1, 2, and 3. So I can see that, therefore, because there are 3 carbons and they are single bonds only, it must be propane. Okay, and then I've got a bromine on carbon 2. So this will be 2 bromo propane, and the number has to come in front of the functional group that I'm talking about. It's not going to be bromo 2 propane because that would cause confusion. Okay, great. And then let's just try one last one. Okay, great. Well done, guys. So a lot of you have said 2-iodopropane. I think the correct answer option isn't actually here. So we'll just go through this one. So again, you want to just identify where are the functional groups. So I've got an iodine over here and I've got a methyl group. So those are my two functional groups. I then want to identify how long is my longest chain. So I can see I've got 3 carbons here. So this is 1, 2, 3. Okay, so I know that this will be propane because there are single bonds only. And then I basically look at my functional group. So I know I've got an iodine at carbon 2, so it would be 2-iodo. And then I've got a methyl group on carbon 2, so it'll be 2-iodo, 2-methyl propane. Okay, so that would be the correct answer. And sometimes there's some confusion about like, why is it not 2-methyl 2-iodopropane, because why can't you write it the other way? So it's just really important to remember that these are done in terms of alphabetical order. So because I comes before M, that's why we put it first, and it would be the same. So even if it was chlorine, chloro, or bromo, that would come before methyl. It's not like a order of priority, it's just based on the alphabet. Okay, so guys, now that we've sort of talked about how we name the compounds, it's very similar to alcohols in that we need to classify them into either they can be primary or they can be secondary or tertiary. So the principles lie the same as they did for the alcohols. But it's just in terms of the functional group, not of the OH, but in this case of the halogen group. So does anyone know in this example, so firstly, what is the name of this compound, and is it a primary, secondary, or tertiary alcohol, haloalkane? Okay, so we've got a few mixed answers. Some of you think this is primary and some secondary. So basically, in this example, what you need to do is, we know that this compound, so we've got 2 carbons, so I know it's going to be ethane. Okay, and I know that there is a chlorine on the compound. So this compound is chloroethane. You don't need to number it because it doesn't matter. There are only 2, so even if the chlorine was over here, it's still chloroethane. Okay, so once I've named the compound, I just want to see, all you have to do is you have to look, where is the halogen? So the halogen is attached to this carbon. Okay, so you have to just look at the carbon that it's attached to. So this carbon is key. And then you want to count how many hydrogens is this carbon attached to. Okay, if it's attached to 2 hydrogens, it will be primary. Okay, if it is attached to 1 hydrogen, it will be secondary. And if it's attached to 0 hydrogens, it will be a tertiary haloalkane. Okay, and this is really important because this, whether it's primary, secondary, or tertiary, affects how it reacts with different chemicals. Okay, so this is chloroethane, and this is a primary haloalkane because we are attached to, this carbon is attached to 1 hydrogen here and 1 hydrogen over here. Okay, so as we can see here, in a primary haloalkane, the halogen is attached to a carbon atom that is attached to 2 hydrogen atoms. Okay, and or you can look at it in terms of alkyl groups as well, which is basically this methyl group here. But I always find that it's very easy to just count the hydrogens, and you will get the answer much quickly. Okay, so let's have a go at this one now. So do you guys think this is primary, secondary, or tertiary? Okay, great. So the majority of you have gone with secondary. So let's just have a look at this compound. So I can see that there is a bromine over here, and there are 3 carbons. So the chain must be called propane, and there is a bromine on carbon 2. So this is 2-bromopropane. Okay, now in order to work out whether this is primary, secondary, or tertiary, I just have to look at the carbon, okay, that the bromine is attached to. Don't be looking at the other ones, otherwise you'll get mixed up. So you just see where is the bromine attached, and I can see that this carbon is attached to 1 hydrogen. Okay, so remember, if it's two hydrogens, it's primary, 1 hydrogen, it's secondary, and 0 hydrogens, it's tertiary. So in this example, it's attached to 1 hydrogen. These 2 are both carbons, so they don't count. So therefore, this one would be a secondary haloalkane. Okay, because the halogen is attached to a carbon atom that is attached to 1 hydrogen atom. Okay, great. So let's just have a go at this last example now. Excellent, well done guys. So this one would therefore be tertiary. So again, just to practice, let's name this one so I can see there is a functional group here and a functional group here. There are 3 carbons, okay, and therefore this will be propane, okay, and I've got 2 functional groups, so it would be 2-iodo and 2-methyl propane. Okay, so I just need to now pay attention to my iodine is attached to this carbon over here. Okay, and this carbon is attached to a carbon, another carbon, and another carbon. So basically the carbon is attached to 0 hydrogens. Okay, and therefore it would be a tertiary haloalkane because there are no hydrogens attached. And this is really important because the fact that there are no hydrogens attached, these compounds, they tend to be much more unreactive because there is no possibility for any hydrogens to be removed or to be added because the CH bond is quite weak. So the tertiary alcohols, they tend to react quite differently, as we will see. And I think we've done these ones. Okay, great. So just a quick recap. So classifying these haloalkanes. So as I said, a primary haloalkane has got 2 hydrogens. And our secondary haloalkane has got 1 hydrogen. And then our tertiary haloalkane has got 0 hydrogens. Or you can do it in terms of alkyl groups. Does anyone have any questions on that, or are you guys okay? Okay, feel free to ask if anything does come up. So as I said, the reactivity of the haloalkanes very much varies depending on which halogen is attached and where in the compound that halogen is attached to. So as we know that haloalkanes, they have got a carbon halogen bond in their structure. So this CH bond is pretty much a non-polar bond because there is a low difference in electronegativity between these 2, as well as the CC, because these are both the same. When we introduce these group 7 elements, okay, it sort of changes things and it introduces a degree of polarity between them. So basically what happens is in anyone, even if it's CCl or let's say Ci, okay, when we look at the electronegativity scale, the electrons, they prefer to sit on the side of the halogen. So the electrons tend to just sit over here. Okay, they don't completely move to that side, but the bond is still there, but the electrons are more attracted towards the group 7 elements. Therefore, this becomes slightly negative because the electron density is concentrated on this side, and the carbon becomes slightly positive. Okay, and that holds the same for all of them. So for the Ci bond, chlorine, iodine, and for bromine as well. Okay, and this slight difference in electronegativity introduces polarity to the structure. It becomes a polar bond, and this influences how it reacts. So as we said, the electron pair in the carbon-halogen bond is closer to the halogen atom than the carbon atom, and that is what makes it polar. So in haloalkanes, the carbon atom has got a slight positive charge, as we can see over here. Now, this slight positive charge, because this carbon is now a little bit weaker and it's looking for electrons, this is what makes the haloalkanes very reactive in nucleophilic substitution, as we will see, because this is very electron deficient, it wants to react with things, and it will react with something that's electron rich, and it's purely because of this difference in polarity. Now the CX bond, so we just call it X. X denotes any halogen, but it's not any specific one, it's just a general term. So this bond is polar, but you will know that, for example, if we had an OH bond, like with an alcohol, so you remember that we had methanol. Okay, if you put methanol, it is soluble in water, okay, because those OH bonds, they form hydrogen bonds in water, and it will very readily dissolve, okay, because of the polar OH bond. However, with haloalkanes, yes, there is some difference in polarity, but it's not enough to make it soluble in water. So even if you take a small compound like chloromethane, okay, just a simple one, like so, this will not dissolve in water, even though there is a slight difference in polarity. It's not strong enough for the OH and hydrogen atoms in the water to react with it. So that is one of the key things to remember, because quite frequently in exams you might be asked to contrast haloalkanes and alcohols. So just remember that these ones are insoluble. Okay, what about their boiling point and their melting point? So what do you guys think will happen as we increase the chain length? So if we increase the chain length of these compounds, so instead of it being chloromethane, okay, we make it chloropentane, okay, and we make it a much larger compound, what do you think will happen to the boiling point from methane compared to chloropentane? Will it increase or decrease? Excellent, well done, guys. So the boiling point will increase, won't it? So as you increase the chain length, so if this is chloromethane, so this is skeletal formula, and this is chloropentane. Okay, the boiling point will increase. Okay, now why does the boiling point increase? Well, because when you boil the compound, you do not break the individual CC bonds, but you break the forces that are between the different molecules, and those are known as our intermolecular forces. Okay, so as the chain length increases, we get an increase in the intermolecular forces, and these are known as our van der Waals forces, which we have covered before. So as the chain length is increasing, you get more intermolecular forces, so more energy is required to break those bonds. Okay, so boiling point will increase with increased chain length. Okay, another property also of the haloalkanes is that the boiling point also increases going down the group, and that is because as you go down the group, there are more electrons in the outer shell of each halogen. Okay, so as you go down the group, fluorine, chlorine, bromine, iodine, and At, as we go down the group, okay, the boiling point increases. So for example, if you just had a compound like fluoromethane versus iodomethane, okay, the iodomethane would have a higher boiling point, and that is because as you go down the group, there are more electrons in the outer shell, and you get more intermolecular forces. Okay, so as we've said, both of these effects are caused by increased intermolecular forces, okay, because the larger the molecule, i.e. the longer the chain length, the greater the number of electrons, and that is true for as you go down the group of the halogens as well, and therefore the larger the van der Waals forces. Okay, great. Does anyone have any questions on that? Okay, great. Well done, guys. So we're just going to do a quick quiz on the naming the haloalkanes and their properties. So if you guys log on to Kahoot. Okay, a few mixed answers on this one. So let's just go through this. So the correct answer here would be secondary. Reason being, you just look at the chlorine, okay, and it is attached to this carbon. So we only want to pay attention to this carbon. Okay, this carbon is attached to one hydrogen, and therefore it would be secondary. Okay, so remember, if it's attached to two hydrogens, it's primary. One hydrogen, it's secondary, and 0 hydrogens means it's tertiary. Great, so again, we look at the chloro, which is our halogen, and we look at the carbon that it's bound to. This carbon is attached to 2 hydrogens, and therefore it is primary. Excellent, well done, guys. So this one is actually a really tricky one because this is skeletal formula. So you just need to count how many carbons there are. So there's 1 carbon here and 1 carbon here, so it's ethane. Okay, and then there is a bromine on 1 carbon and an iodo on the other. So therefore it's 1 bromo, 2 iodoethane. Great, well done. So haloalkanes have got hydrogen atoms that are substituted by one or more halogens. Okay, so it's not carbon atoms, guys, because carbon atoms form the main chain length, but the carbon still exists. It's just that instead of a hydrogen, you've got a halogen. Fantastic. So that one is nice and easy. That is chloromethane. So this one is trifluoromethane. So for those of you guys that have put 1, 2, 3, when there's only one carbon, okay, you don't need to you don't need to put the numbers, because it doesn't matter whether this is 1 or this is 1 or 2 or 3. It's all the same, because there is only one carbon. You only need to put the numbers after ethane, because that will dictate their position. You don't do it for methane or ethane. Excellent, well done everyone. Yeah, that is 1,2-dichlorobutane, okay? And this is 4 carbons, so we know it's butane. There are 2 chloros, so you have to say di. If there were 3, you would say tri, and these are on carbon 1 and carbon 2. Okay, and it's just important to know that in this molecule, we are naming it going backwards, like we put 1 here and 2 here. We don't put 1 here and 2 here, 3 here, 4 here, because then it would be 3,4-dichlorobutane, and that just makes the name much longer, and we try to minimize the numbers. So well done, that's why it's 1 and 2. Excellent. So just looking at this one, so this one is 1-bromo, 2-iodo propane. Okay, and we just name them in sequence. Yeah, that's excellent. Okay, well done. So it looks like Simran is in the lead, but well done to all of you guys. Most of you got all of them right, so I'm really pleased with that. So we'll just continue where we left off. Okay, so guys, we have got a good understanding of what haloalkanes are and how to name them and classify them. So we're going to talk now a little bit about their reactivity. So haloalkanes, they commonly react with nucleophiles. Okay, so this is different to each functional group in organic chemistry reacts with something else. So like alkenes, they commonly react with electrophiles. And this is a different topic, but it's just each different group of compounds in organic chemistry, they react with different types of substances. So a nucleophile is an atom or a group of atoms that is basically electron rich, okay? So when you guys think of a nucleophile, I want you guys to think of something that has got lots of electrons and it wants to give it away, okay? So the strict definition is that a nucleophile is an atom, so it can be one on its own, or it can be a group of atoms that is basically attracted to an electron deficient carbon atom, okay, where it donates a pair of electrons to form a new covalent bond. Okay, so don't be fazed by this, guys. So basically, all we're saying is that a nucleophile, it is electron rich. Okay, now because it's electron rich and it's got these electrons, it wants to give them away. Okay, and what is it going to give it away to? Well, it will give it to something that is electron deficient. So something that doesn't have electrons, because obviously opposites attract each other. So does anyone know any examples of any nucleophiles? Okay, some of you have said ammonia, great. Any other ideas? Phosphorus, not quite. Phosphorus would not be a nucleophile. Cyanide, CH3, so methane, no, methane is not a nucleophile. Sulfuric acid, not commonly used in these reactions. Sulfate, yes, excellent, and hydroxide, well done. So nucleophiles are anything that have got a spare pair of electrons. Okay, so common ones are hydroxide ions, and this is what we will really be looking at. So you guys will know that hydroxide ions are OH minus, right? They are OH minus, reason being they've got a minus charge because they've got a spare pair of electrons. Okay, it's like sodium hydroxide. You know, you guys know NaOH. Na is Na plus and OH is minus. Okay, reason being because OH has got these pair of electrons, and this pair of electrons make it electron rich, and it wants to give it away. Okay, so we will be looking at hydroxide ions in detail. Another common example is water as well. So you don't have to have a charge on it for it to be a nucleophile. You just need the pair of electrons. So similarly, H2O has got a lone pair of electrons on the oxygen. So if just to make that very clear, this is oxygen. Okay, this is it is a covalently bonded molecule. I'm sure you guys know this, but there is a lone pair of electrons. Okay, and that, sorry, that's wrong. And that is basically what we're talking about. That is the 2 dots. And we've got a really good question which says, does it matter where the pair of electrons are, either on the left or the right? Strictly speaking, it doesn't matter, but you will still get the mark, but it's just good to place it where the lone pair of electrons actually are, because like if you put it here, say if I wrote H2O, it doesn't really make sense because there is no lone pair of electrons on the H. Okay, they exist on the oxygen. But that's a good question. And also ammonia, as you guys rightly said, which is NH3. So ammonia looks like this. Okay, and then ammonia has got 5 electrons in its outer shell. So these are all bound to hydrogen, and then it's got that lone pair that sits here at the top. Okay, and this lone pair of electrons, again, it makes it electron rich. Okay, so why does all of this matter? So basically, do you guys remember that earlier on we said that the haloalkanes, because of that difference in polarity, okay, let's just take the CCl bond. The difference in electronegativity makes this slightly positive and this slightly negative. So the carbon atom in our haloalkane bond, it has now become electron deficient. Okay, because those lone pair, the pair of electrons in this bond, they sort of are just sitting towards this side. Okay, they're not completely moved there. It's not an ionic bond or it's not separated, but they're just sitting on this side. And this means that the carbon is a bit lonely and it needs some more electrons, okay, because it's got a positive charge. And this is where our nucleophiles come in. So we said our nucleophiles are, for example, OH. Okay, they could be NH3. Or they can be H2O. Okay, I'm just going to write that over here. So in the exam, they might give you any nucleophile, an unfamiliar one. So this is why it's really important that we become confident with the ones that we know. Then you can apply it to any nucleophile because there are millions. So this is electron deficient. These are nucleophiles. Okay, and these are electron rich. Okay, as I've said, these have got a lone pair and they want to react with something that doesn't. So essentially, all of these haloalkanes, they take part in these reactions whereby the lone pair of electrons on the nucleophile is attracted to the carbon. Okay, all of these, they react in the same way, it's the exact same thing, such that these are so there is a very strong attraction between the lone pair and the carbon, such that there is a replacement of the bond. So instead, we then get a COH, and the chlorine gets removed, or we get a CNH3, or we get in H2O, it's the same thing, you get a COH. Okay, so what has happened is that because of the strong attraction between the nucleophile, the electron-rich nucleophile, and the electron-deficient carbon atom, there has been a substitution reaction. Okay, so these reactions that we're going to talk about the mechanism, it is a substitution because instead of a Cl, we're replaced with something else. Now, because we used a nucleophile for the substitution, we call this nucleophilic substitution, okay? And that is the basis of what is going on. So I'll just erase that. So as I said, when a haloalkane reacts with a nucleophile, the nucleophile will replace the halogen in a substitution reaction. Okay, and we then get a new compound being formed, which contains a different functional group. It can be OH, it can be NH3, whatever they can give you. They might give you sulfate, which is a bit rare, but any other functional group, whatever was on the nucleophile. Okay, and as we said, this reaction mechanism is known as nucleophilic substitution. And in organic chemistry, there are many other very interesting reactions like electrophilic addition reactions and things like that. So it's really important to become very clear with this terminology. This is electron rich. Okay, and this is substitution. So it's basically a swap, okay? It's not an addition reaction and it's not elimination. We are swapping things around. Okay, guys, so we're going to talk a bit about the exact mechanism and drawing out the curly arrows and the movement of the lone pair. But if we just take a quick break, because I know it's 10:45, so we'll just go for a quick break. And if you guys come back at 11, and we will carry on, but feel free to leave any questions in the chat, and I'll see you back at 11. Hi everyone, welcome back. So I hope you had the chance to grab a quick drink. So we will continue where we left off. So as I said, haloalkanes take part in nucleophilic substitution reactions, and a very common example of a nucleophilic substitution reaction is that of hydrolysis. Okay, so what does hydrolysis mean? Well, essentially hydro meaning water, and lysis meaning breaking. So this is a chemical reaction where we are using water to break a bond in a molecule. Okay, that is the definition of hydrolysis. And hydrolysis is a really common example of nucleophilic substitution, and it's definitely one that you should be very confident in drawing the mechanism out from, which I will show you guys. So essentially what happens is a water molecule or hydroxide ion comes along and it basically breaks the bond of a molecule. And this results in that molecule being split into two things. Okay, it's lysis and it's being broken down. Now, specifically with haloalkanes, when we hydrolyze a haloalkane, basically what happens is that our halogen atom, i.e. our chloro, bromo, or iodo, is essentially replaced by an OH group. Okay, that is the water molecule or the hydroxide ion. Okay, so basically what happens is instead of having a CCl, okay, we end up with a COH. Okay, so we can just pretend, let's say that this was chloromethane. And what happens basically is that we react this chloromethane with some water or hydroxide ion, and we end up getting this compound, which is methanol. This is an alcohol. Okay, and this is an example of a nucleophilic substitution. Okay, so how does this actually happen? So basically, I'm going to show you guys the reaction mechanism and we're going to draw it together. So what I would suggest is instead of just watching me, if you have a bit of paper, if you just draw out this molecule, so this is chloroethane, and you just draw out a hydroxide ion, and you can just follow what I'm doing and it will be much easier for you to appreciate. So I'll just give you guys a moment to just draw that out. Okay, so as I said here, we have got a hydroxide ion. Okay, this is a nucleophile, okay, because it has got a lone pair of electrons here, and it is electron rich. Okay, we have then got over here we have got chloroethane, right? And we said that because of the presence of the halogen, there is a difference in polarity between these two elements. So the electrons, they tend to sit towards the chlorine. So our carbon becomes slightly positive and our chlorine becomes slightly negative. Okay, there is no polarity difference in the rest of the molecule. They're all fine. It's just the carbon that is attracted. It's just the difference between the carbon and the chlorine. Okay. Now, what does this create? Well, if we then start to mix this chloroethane with this hydroxide ion, if you pour some water on it, essentially there is an attraction between the lone pair of electrons on the nucleophile and the slightly positive carbon atom. Okay, so basically what happens is the electron pair moves, and we denote the movement of an electron pair with a curly arrow. So you need to be very careful about how you draw these curly arrows. So you draw a line from your electron pair going to the carbon atom. Okay, and this is a curly arrow. So if you've done this before, basically a curly arrow shows a movement of electron pair. Okay, and you can't just be drawing these anywhere, or you won't get the marks if you don't write this out really clearly. So the arrow must go from the electron pair, and the arrowhead must go directly to the element that is receiving the electrons. You can't just draw it in the middle of this, or like on the side. You need to show that it's going to the carbon. Okay, we have to be strict with that. Okay, so what basically happens, so the electrons from the OH really like this carbon because it's slightly positive. And essentially what happens is these two tend to form a bond with each other because they are very much attracted to one another. Okay, so what then happens is that we instead of getting a Cl, okay, we we then get a COH bond. So we get a COH bond instead. Now, the only way that that can happen is that this CCl bond has to break, doesn't it? Now, the way that it breaks is that the electrons in this bond, they go to the chlorine completely. So you'll remember that I said earlier that there is a difference in electronegativity such that the electrons, they're just sitting by the chlorine, okay? What that means is that there's an electron cloud and they just tend to sit around here. They're not actually completely moved away. But when this bond breaks, the electrons completely move towards the chlorine atom and we get a chloride ion. Okay, so again, in red, I will draw my curly arrow. And essentially what happens, so the electrons that are sitting in the CCl bond, they move to the Cl. Okay, that electron pair moves, and that is what allows the bond to break. Otherwise, the bond won't break. Now, if the electron pair has moved to the Cl, what I will be left with is a chloride ion. Okay, this is not slightly negative. It's not slightly negative anymore. It's completely negative because the bond has broken and the electron pair has moved. Okay, and that is basically nucleophilic substitution. And then you just have to write out the rest of the atom over here. Does anyone have any questions on this so far? I will show you guys it again, but we've got a question which says, why are we drawing an arrow from the OH to the C? We're drawing an arrow from this because there is a reaction taking place. This is very electron rich and it's attracted to this this electron deficient carbon atom. So that's why the electron pair moves from the OH to the carbon and it allows a bond to be formed over here. Okay, so you can just see that very nicely over here. So we form an OH and we form a chlorine. Okay, so this is very typically a 3-mark question where you get 1 mark for basically showing that there is a difference in polarity. Okay, you get another mark for showing the movement of the electron pair. And you get another mark for showing the movement of the electron pair over here. Okay, so it's kind of a 3-step process. And in terms of your products, you will form this COH bond and you form a chloride ion. And we've got a very good question which says, why are there 3 carbons? Sorry, that's a mistake actually. This should just be 2 carbons. We've added on 1 by accident. So you're right, this should just be a H here. It's meant to be the same product. Only the OH and the Cl will change, so well spotted. And we've got a question which says, do we need to put a slightly negative on the OH? No, you do not put a slightly negative on the OH because this is not slightly negative. This is fully negative. Okay, this is an ion. Slightly negative is for covalent compounds when there is a difference in polarity. This is an ion, so it's not slightly negative. Okay, so this is the mechanism that is shown here very nicely in your textbooks. As you can see, we've got the lone pair of electrons moving from here, and the difference in polarity shows the electron movements here when this bond breaks, and we are left with our products. Okay, so sometimes you may also be asked to just kind of describe what's going on. So I'll just go through this again. So our nucleophile, which is our OH, approaches the carbon atom, okay, attached to the halogen on the opposite side of the molecule from the halogen atom. So it's just approaching it from here. It doesn't really matter. You can also just showing it from here, but they've just shown it on that side. Now, a lone pair of electrons on the hydroxide ion is attracted and donated to the slightly positive carbon atom. Okay, so this lone pair of electrons here, it wants to go to this carbon and it gives the electrons. And this is what allows a new bond to be formed because the electrons are donated here and we get a COH bond being formed. But what about this chlorine? Okay, now this carbon halogen bond, this CCl bond, it breaks by something called heterolytic fission. Okay, and I will explain to you guys what that means. So we have hetero meaning different and lytic meaning breaking. So there are two things that there is homolytic fission and there is heterolytic. In homolytic fission, the electrons are shared equally, whereas in heterolytic fission, they are shared unequally. So basically, sometimes what happens is that when a bond breaks, let's say, for example, we've got a Cl-Cl bond, okay? When it breaks by heterolytic fission, by homolytic fission, what happens is that one electron will say, okay, I'm going here, and one electron will say, I'm going here, okay? So you basically end up with a Cl and a Cl, okay? This is homolytic fission, meaning same. Now, what happens in heterolytic fission is in this example, so we've got a CCl. So instead what happens is that both of the shared pair of electrons that are sitting in this bond, they say, actually, we both want to go to Cl. So both of the electrons go there, okay? And essentially what that means is that we are left with a C and a Cl minus, which has now got 2 electrons, okay? And this is known as heterolytic fission. So it's a breaking of a bond where the electrons are not split evenly. So hetero meaning different and lytic meaning breaking, okay? And we will see homolytic fission when we look at the ozone layer and free radicals and all of that. But for now, you just need to remember that this the electrons are not being shared evenly and they both go to the chlorine. And then finally, the new organic product that we make is an alcohol, of course, because we've got an OH group, and this is our functional group for alcohols. Okay, and we also get the formation of a halide ion, which is Cl minus. Okay, so it's really important that you guys realize that this is an ion because the pair of electrons have gone to the chlorine, both of them. Okay, and that was in heterolytic fission. Okay, so again, we can just see that over here. And this is just a top tip. It's really important that the curly arrows that you draw, they need to start and end at the correct places, okay? Because they're really picky about this because this does show where the electrons are going. So a curly arrow, as I said, shows the movement of electron pairs. Okay, it's not just any kind of arrow. A curly arrow is very specific. And curly arrows start from either a lone pair of electrons or a bonding pair of electrons and point to the atom to which the electron pair moves. So it's just like normally how you show an arrow is showing how you're going from A to B, right? So it's the same thing. It's just showing where the electrons are going. So they're going from here to here. Okay, and similarly, they are going from, because the electrons are sitting in this bond, you have to draw it from the middle of the bond and it goes over here. So like if you just drew it kind of like, you know, just sitting up here and like this, you wouldn't get the mark. You need to show that it's touching the bond because the electrons are moving from this bond to the chloride. Okay, so we've just got a little video which shows you exactly what is happening. So this is the halogen and this is my nucleophile. So we can see that the electron pair has moved from here. Okay, this bond then breaks and we get the substitution of our alcohol over here and we get the removal of the halide ion. Okay, so this red blob can be our OH minus and this green one would be the Cl. So hopefully you guys can see that. So do you guys have any questions on nucleophilic substitution? Because I know if you haven't done it before or it's been a while, it's a bit tricky to understand. Okay, let's have a go at a question then. So this is a 3 marker. So name and outline a mechanism for the following reaction that occurs in process 1. Okay, so firstly, guys, tell me what process, what is a name given to this reaction that is taking place? Great. So some of you are saying substitution. So specifically, this is nucleophilic substitution, right? So basically, because as I said, so even if you've got the principle clear in the exams, they can give you like complex molecules. So don't be phased by that. What you can see here is that you can see that there is a bromine group. Okay, so this is a haloalkane. Okay, that's all we need to know for now. We also know that this is a OH, okay, so this is a hydroxide ion. What do we see happening here? We're left with 2 products where this has now become an alcohol, okay, and we have got a Br left behind, we've got a halogen. So basically what has happened is this is a substitution reaction, and our OH is our nucleophile. So this is nucleophilic substitution. And we've got a few questions which are saying, like, doesn't this have to be an ion? Like, doesn't it have to be OH minus? So when we draw out the mechanism, we show that for simplicity. But in real life, if you're going to mix these 2 together to make an alcohol, you have to use a solution. And when you use this in a solution, the NaOH basically splits up such that you get Na plus, okay, and OH minus. So it is still an OH ion, but it's just that when you write it out, and we do show that there is a sodium, but it doesn't take part in the reaction. So it's asking you to outline a mechanism. So what that means is that we need to write out the we need to draw out the mechanism. Okay, so what I'm going to do is, if you guys have a go at doing it, I will just sort of help you guys show the initial molecules so you know what I'm doing. So basically I'm drawing this molecule over here. So it does say outline a mechanism. So in the mark scheme, it's showing that you need to draw out the curly arrows and draw out the whole mechanism as well as naming it. So you need to show the movement of the electrons. So whenever we do the mechanisms, we just want to show what's taking place. So like, I'm not going to write NaOH. I'm just going to write OH minus. Okay, because when you do a reaction mechanism, you don't try and draw everything out. You only show what's actually happening. So that's why we show this clear bond over here, because this is where the reaction is taking place. So I'll just give you guys, if you guys just draw this, I'll give you just a minute to draw out what you think will happen next. So what I'll do is I'll show you guys, obviously I know you guys can't show me your answers, but I will show you guys the model answer and how to do it. And if you guys just match up and compare yours to mine, and if you don't understand, then obviously please let me know. Okay, so there are 3 steps to this, and we start off with the basics. So firstly, I want you guys to remember that this is a polar bond. There is a difference in polarity. This is slightly positive, this is slightly negative. Okay, that's 1 mark done there. This is slightly positive, and this is our nucleophile. It's electron rich. So my curly arrow will go from the lone pair to the carbon. Okay, excuse that little squiggle, it doesn't matter, but it's just show the arrow there. Now, these two want to form a bond with each other. If they want to form a bond, this CBr bond needs to break. Carbon can only form 4 bonds. It cannot form 5. There can't be an OH and a Br just chilling with the carbon. One of them has to go. So this CBr bond breaks. How does it break? By heterolytic fission, whereby both of the electrons pair in the bond move to bromine. Okay, and that is my second mark there for this arrow. And then what will I be left with? Well, then I will have a COH bond that has been formed over here, and then you just draw out the rest of the molecule. So don't worry too much about that. These are just H's, and there's another Br there which is not taking part in the reaction. Okay, and we form this COH bond, plus we form a Br, but this is not a bromine atom, it's not a slightly negative bromine, this is a bromide ion. Okay, it's ionic because it has taken both the pair of electrons and it has become a charged ion. Okay, so this process is known as, this is just extra obviously, so if you, and then this one would be your third mark, okay, showing that this is an ion. So well done if you got that. This is known as nucleophilic substitution, as we have said, and this process here is heterolytic fission. Okay, any questions on that, guys, or are you feeling happy with that? Okay, so why is the CBr bond on the left not affected? So that is actually a really good question. And I don't really know why they haven't shown it taken part in this reaction. It's very interesting because they've just shown substitution of one alcohol. So I don't know why I don't know if they've just done that to keep it simple or what it is, but they've only shown it for one, I think because they don't want you to draw out two. But in reality, if this reaction were to take place, both of them would become substituted. And is it always a hydroxide nucleophile? No, it's not. Sometimes we can get NH3 as well and H2O. So I will show you guys some more examples of different nucleophiles. And would putting NABR at the end correct? So if you put NABR instead, yes, you would get the mark for that, but I'll just show you the mark scheme. They have shown that you have to do a BR minus, and that is basically because when we do reaction mechanisms, we basically show exactly what is happening. This is just our word equation for the overall process, but reaction mechanisms are specifically showing the movement of electrons and the movement of ions. So it's best to show that this is a BR minus because you did not put a sodium here. So where did the sodium come from here? Okay, it wasn't on the left, so you can't just bring it in on the right, even though it's in the here, but it's just a spectator. It doesn't take part in the reaction. So you should just write BR minus. Okay, so just a few definitions to just really consolidate what we have learnt. As I said, a nucleophile is an atom or a group of atoms that is attracted to an electron deficient carbon atom or any other electron deficient atom. And in heterolytic fission, this is when a covalent bond is broken and the shared pair of electrons is taken by one of the atoms. And curly arrows basically show the movement of electron pairs. So this is just because I know hetero and homolytic fission might mean and it might be a new thing for you guys. So you can just see that over here. If we have two elements that are joined together in a covalent bond, A and B, so you can see that heterolysis is when the electron pairs are just moving to one. Okay, so you then form two ions. You get A plus and B minus, but in homolytic fission, one electron will say, okay, I'm going here, and the other electron will go over here. Okay, so that will give you something called free radicals, and we'll talk about that in the afternoon. Okay, so this is heterolysis and homolysis. Okay, so as you guys said, so there are some other examples of nucleophilic substitution with haloalkanes. It's not just with hydroxide ion, although that is the best one to understand it with. So one that might come up is that of cyanide ions, which I think you guys actually mentioned. So basically, when the haloalkanes or halogenoalkanes are warmed with an aqueous alcoholic solution of potassium cyanide, these are just the specific conditions that it needs, you actually get a nitrile being formed. So basically cyanide ion, in case you've not heard of it, so cyanide is basically, it looks like this, it's a complex molecule, it's triple bond, and it's CN, like so, and it's got a negative charge on it. But usually what you can just write is you just write CN like so. So as you guys can see, it doesn't really matter, like even when you had OH, it's just OH, right? Or when it's NH3, it's NH3. So all we're trying to show is the lone pair of electrons. So for cyanide, it's just CN. So don't worry about the bonding and what is actually happening in between them. It's actually just a triple bond like so. So as I said, the nucleophile is the cyanide ion CN. Okay, so let's just have a look at an example. So let's just say I take, so again, if you guys just want to draw this along with me, so instead of a chlorine, let's just use a bromine. Okay, so this compound here is bromoethane, right? And let's just say I dissolve this bromoethane in an alcoholic solution of potassium cyanide. So potassium is KCN. The potassium bit is just like a spectator. It's just like the sodium in the previous example. It doesn't take part in the reaction. So I then just draw a CN here. Okay, and like so. Okay, so guys, what do you just have a go at drawing what you think will happen, and what products you will form and what it will look like? Okay, so let's go through this one together. So don't worry if you get an unfamiliar ion in the exam or something that you've never seen. If your principles are clear, you will be able to tackle this with ease. So again, identify this is a polar bond. Okay, this is slightly positive, this is slightly negative. Okay, there is a lone pair of electrons here on this ion, and these get attracted to the slightly positive carbon. So I draw my curly arrow over here. Now for this bond to form, this one needs to break by heterolytic fission. Okay, exactly the same thing. And therefore I will then be left with a C carbon that is attached to this CN, okay, and a bromide ion. Okay, so this is a little bit confusing, like why there is a carbon to a carbon, but this is the property of cyanide, and it basically is, what it actually is it's like a C attached to a C, and then there are, it's like that, it's like a triple bond between this CN, but you can just write CN and that's fine. So we've got a question which says, wouldn't C to Cn be a triple bond? So the triple bond is between the carbon and the nitrogen of this thing, okay? So potassium cyanide is this C triple bond N. So the triple bond is between this C and N. So you can just draw a triple bond here if you want to, but you can also just write Cn, you get the mark for that. And this CN, I know it's cyanide, but it's actually called nitrile. This CN group, we name it as nitrile. So this is a nitrile group. And because there are, so this would be like ethan nitrile because there are 2 carbons over here. But you don't need to worry about the naming of cyanide ions. It's just to show you that there are many nucleophiles, and this is an example of one. Okay, we've got a question which says, what happens to the potassium ion? So the potassium ion is basically just a spectator ion. Okay, so by spectator, it's sort of like it sits in the audience and it just watches what goes on. Okay, like when you go to watch a match, you don't take part in the match, you're just a spectator, you're just watching. So the potassium is just there to like dissolve the cyanide in, and it doesn't do anything in the reaction. So we don't write it in reaction mechanisms, but you can just say, for example, so like it would say if this was KCN, okay, then basically that potassium, it goes and reacts with the bromide and you get KBr. Okay, so if I were to write a word equation, it would basically be CH2 CHBr reacts with KCN, okay, giving me CH2 CHCN plus KBr. Okay, it's just like the sodium that we saw before. Nothing is happening to the potassium, it's there, but in our reaction mechanisms, we only draw what's actually going on and the movement of electrons, and potassium doesn't take part in that, so we just leave it like so. So I hope that answers your question. Okay, do you guys have any other questions on that? Okay, and that is just the answer there. Okay, so let's just have a go at a few exam questions now. So they are, some of them are fairly straightforward, they're not as challenging, so don't worry. So let's just go through this. So a student reacted 8.72 grams of bromobutane with an excess of hydroxide ion. The student produced this much of butan 1-ol. Okay, in this reaction, the hydroxide ion acts as a nucleophile. What name is given to this type of reaction? Okay, tell me, guys, what do you think? Excellent, well done, guys. So this is a nucleophilic substitution, well done. And this is also an example of a hydrolysis reaction as well, as we said earlier, because we are using water to break a compound. So actually you could say either of these things. Okay, explain the term nucleophile. Okay, what is our definition of a nucleophile? Excellent. So you guys are saying a species that's attracted to an electron deficient species, an electron pair donor, it's electron rich. Excellent. So you can just get the mark here for saying electron pair donor or electron rich species, and just make it clear that it's giving the electrons away. Okay, so it's electron pair donor, and it's electron rich or has a lone pair of electrons. Any of these would be fine. Okay, fantastic, well done, guys. So okay, and then outline the mechanism for this reaction, show curly arrows and relevant dipoles. Okay, I know we've done this to death, so this will be the last question on this. So basically they're saying bromobutane with an excess of OH minus. Okay, so we've got bromobutane and an excess of OH minus. So I won't help you guys. So if you guys are able to just draw these on your own and have a go, and then I will show you guys the correct answer. And butane is 4 carbons, that's correct. If you guys ever get mixed up of like what's propane, what's butane, what's methane, just remember monkeys eat peanut butter. So methane is 1, ethane, propane, butane. Okay, so I will just start drawing this out for you guys. So don't worry if you haven't finished yet. I'm just going to make a start. So we have got bromobutane, right? So butane has got 4 carbons, and there is a bromo on the end. That is a bromine. So this is 1, 2, 3, 4. And just for extra points, guys, this is, what do you guys think? Primary, secondary, or tertiary haloalkane? Excellent, this is primary, well done. Well done, guys, I'm really pleased. Okay, so we have drawn out our bromobutane, and they said they react it with OH minus. Okay, so OH minus has got a lone pair, which you do draw on the side of the O. Okay, and now I'm going to draw out my reaction mechanism. So remember, this is a polar bond, slightly positive, slightly negative. My electrons will move to the carbon. It's attracted to this carbon atom. It wants to make a bond here. This one needs to break by heterolytic fission, and therefore I will then be left with an alcohol, okay, and a bromide ion. So I will then be left with a COH, okay, and a Br minus ion. Okay, that would be a bromide ion. And that is basically it. So you get 4 marks for that. So I'll just show you guys the mark scheme. So they've just done it here like this. We draw it out. I think it's easier if you draw it out fully. So correct dipole, this is our dipole. Curly arrow from the O to the C. Okay, and then we did that. Curly arrow to show movement of bonded pair. This one over here. And Br minus as a product. Okay, and that is 4 marks. So hopefully you guys got that one. Do you guys have any questions on that or you don't understand? Okay, great. So we'll just move on. So this reaction that we've been talking about, that we just showed, where the haloalkane becomes an alcohol. Okay, that is basically using OH. Okay, and very commonly we use sodium hydroxide. So this reaction that is taking place, which we've talked about the mechanism for, it's usually very slow at room temperature. So we heat it under reflux. I think we talked about reflux in our last session, where you continue to evaporate and condense it, and it allows us to obtain a good yield of product. Okay, so for example, the equation for the hydrolysis of 1-bromobutane, which we just did, is like so. Okay, so we have a Br and it gets swapped with the OH. Okay, so you might be thinking, okay, why are we talking about this again? So we've talked about the reaction mechanism, but quite frequently we want to learn about the properties of the reactions with different carbon halogens. So depending on whether it's a Cl or a Br or an I, the rate of the reaction varies, and the rate of the reaction varies, and we can talk about why that is. Okay, so basically what happens is that, as we've said, that in this reaction, that carbon halogen bond is broken and we form an alcohol. Now, the rate at which this is happening will depend upon the strength of the carbon halogen bond in the haloalkane. So obviously, if the CBr bond is stronger, the OH is going to struggle to work its way in. Okay, whereas if it's a CCl bond and the bond is weaker, it's easier for it to go through. So we'll just talk about the differences. So the CF bond is actually the strongest. Okay, this is at the top of the periodic table, and the Ci bond is the weakest. So this graph is showing bond enthalpy. So enthalpy is the energy required to break the bond. So basically what it means is that less energy is required to break this Ci bond compared to like the carbon fluorine or the carbon Cl. So obviously this reaction will be quick and this reaction will be slow, okay, because obviously you don't need much energy to break it, so it will do it more easily. So from these bond enthalpies, we basically predict that, yes, so iodoalkanes, obviously they will react faster than bromoalkanes, and bromoalkanes will react faster than chloroalkanes, like so. And fluoroalkanes are actually very unreactive because a large quantity of energy is required to break this CF bond. Fluorine is a very interesting chemical, and we don't usually use it in many things. It's involved in the ozone layer. For these experiments, we just use these three. So a really common experiment, which actually you might have done very briefly at GCSE as well, is where you can compare the rate of the hydrolysis of 3 haloalkanes. So you just take each of these, like it doesn't matter if it's butane, propane, whatever, but you just take the chloroalkane, a bromoalkane, and an iodo one, and you just see like how quickly will these turn into an alcohol. So just from judging, guys, which one is going to be the quickest reaction? So we've just said the bond enthalpy, so which one is going to be the fastest from these? Okay, so some of you guys are saying chlorobutane and some of you are saying iodo. So guys, we just said that iodobutane, okay, has got the smallest bond enthalpy. So this reaction will be the fastest. Okay, and this chloro one will be slowest when we compare these three, okay? So this reaction is slow and this reaction is quick, okay? That is the way we're going. Now, the very common experimental techniques that we can use to compare these is using aqueous silver nitrate. So basically what we do is, in general, what is happening in all of these haloalkanes is that the X, which is our halogen, is basically being swapped to an OH, right? And you're getting the Br minus or Cl minus or whatever being formed, okay? So X represents any of these halogens, And if we want to see like which reaction is happening the quickest, or if you want to try and identify an unknown haloalkane and you want to say, oh, I've got this haloalkane, I don't know which one it is, you can do this experiment. And basically what we do is we put this haloalkane with aqueous silver nitrate and ethanol. Okay, so what I do is, let's say in my test tube, I've got some unknown haloalkane. Okay, so we just pretend, let's just say it's blue, which it isn't, but this is just, let's just say this is CH3X. Okay, so this could be like chloromethane, it could be iodomethane, or it could be bromomethane as well. I don't know what it is. So basically what you do is you then just mix some silver nitrate, which is AgNO3. Okay, you mix it in here, and you also put in ethanol. Okay, why do we put ethanol? Because ethanol will have it basically allows it to dissolve much more easily in the silver nitrate, otherwise it's not very reactive. So you just mix them together, and essentially what will happen is that the Ag, the silver will separate. So AgNO3 looks like this. Okay, and then we have, basically what happens is the silver, the Ag plus ion from the silver reacts with our halide ion. So like if we imagine that this was bromine, it will react with Br minus. Okay, that is this halogen here. Okay, and you would get AgBr. If you put Ag with Cl minus, okay, you get AgCl. And if you put it with iodine, you would get AgI. Okay, so this is like silver bromide, silver chloride, and silver iodide. Okay, so what's the point of this? Well, basically each of these form a different color. Okay, they form a precipitate. They basically form a solid at the top when you react it, and for each of them it's a different color, and I will talk about the colors, and that's basically how you know what solution you had in the beginning. So as we said, so as this reaction takes place, the halide ions react with the Ag plus, okay, to form a precipitate of a silver halide. Okay, and this is basically what is happening. You get Ag plus, which is our silver ion, and it reacts with X minus, which is any halide, and you get a solid, you get a precipitate. Okay, so basically what happens is that depending on what thing you had, what haloalkane you had, you get a different color. So basically when with chloro, you get a white precipitate. With bromine, you get a cream precipitate. And with iodine, you get a yellow precipitate. So it's basically white, cream, yellow. And you do need to know these going down the group. So I just remember C, Br, and I going down the group. And this is white, cream, and yellow. That's not really a way to remember it, but I've just done this for so many years, so I remember it. But you just, if you read it a few times, hopefully you should be able to as well. So remember we said that as we go down the group, so the bond enthalpy is higher for chlorine compared to iodo, right? So the rate at which it forms is also different. So with chloro, this reaction is slow because chloro has got a higher bond enthalpy. Okay, so a white precipitate forms very slowly. With the iodobutane, remember on the graph, the bond enthalpy was very low. Okay, so a yellow precipitate forms rapidly, and bromobutane sits in the middle, so the rate is in between these two. Okay, so as we can see, so the rate of hydrolysis, i.e. the rate that this reaction is taking place, increases as the strength of the carbon-halogen bond decreases. So the bond enthalpy is decreasing. Okay, so as we've said, these observations are explained by considering the bond enthalpies of the carbon-halogen bonds. Okay, and the compound with the slowest rate of reaction is the one that has the strongest carbon-halogen bond. So obviously the strongest bond is this one. Okay, because it reacts slowly and it forms a white precipitate. And 1-iodobutane reacts the fastest and it forms a white, cream, yellow. So iodo forms a yellow precipitate. So this is white, this is cream, this is yellow. Okay, and this reaction is slow, this one is medium, and this one is fast. Okay, guys, and that is basically nucleophilic substitution and the reactions of haloalkanes. So let's just do a quick quiz, because I know it's quite a lot of information I'm giving you guys. Okay, we'll just get started. If you haven't been able to log on, the pin is at the bottom of the screen. Excellent, guys. So a nucleophile must have a lone pair of electrons. It does not need to have an oxygen. So commonly they do, but that's not a criteria. Excellent. So a nucleophile is an electron pair donor. It's not attracted to negative centers, guys. And a nucleophile is attracted to a positive charge, like that slightly positive carbon. So that is wrong. Excellent, well done. So this has got a positive charge, so it cannot be a nucleophile, okay? Because it by definition that means it's not electron rich if it's got a positive charge. Excellent. A nucleophile will donate electrons. Amazing, well done. That is very true. Excellent, guys. So it is heterolytic fission. Hydrolytic is actually something random that's there to confuse you. So hydro means water. So I know it sounds similar, but it's actually heterolytic fission. Hetero meaning different, and there is an uneven distribution of the electrons, whereas homo meaning same. Okay, homolytic fission generates free radicals, which is different. Oh, okay, so the correct answer is bromide. So guys, it goes chloro, bromo, iodo, and it's white, cream, yellow. Okay, so cream is in the middle and it is with bromine. Well done, guys. Okay, so let's just do a few more questions on this, and then we can all go for our lunch breaks. So where were we? Okay, so let's just have a look at this question. So which one of the following statements explains best why fluoroalkanes are the least reactive haloalkane? Okay, A, B, C, or D? What do you guys think? Okay, so most of you guys are saying D, some of you saying C. Okay, so let's go through this one. So basically, we said that, remember, the fluoroalkanes, they've got a very high bond enthalpy, remember? So just remember that graph in the beginning. This was our bond enthalpy. Fluorine was at the top, chlorine, bromo, iodo, and it was going down like so, right? And the reactivity is the least on the fluoroalkane because the bond enthalpy is very high. It's hard to break that bond, so therefore it is the least reactive. So your correct answer is D. It's nothing to do with the polarity. Okay, whether it's polar or not, that's not talking about the strength of the bond. It's got nothing to do with it. This is not the most stable halide ion. That's not true. And fluorine is much more electronegative than carbon. That's also got nothing to do with it. So your correct answer is D. Okay, so let's have a go at this one. So a student carried out an experiment to study the rates of hydrolysis of some haloalkanes. Okay, in the experiment, 2 different haloalkanes were placed in separate test tubes containing silver nitrate. So this one, we've seen this reaction. The haloalkanes reacted with the water and the silver nitrate. The student timed how long it took for the first appearance of the silver halide precipitate in each tube at a constant temperature. Okay, the student obtained the following results. State the meaning of the term hydrolysis. Great, so you guys are saying using water or hydroxide to break molecules, breaking of a bond through the addition of water. Excellent. So you can just say splitting, okay, or breaking of bonds by using water. Okay, yeah, that is the answer that they have given. Okay, great. State the color of the precipitate formed when iodide ions react with silver nitrate and write the simplest ionic equation for this reaction. All right, guys, what is the color first? Is it white, cream, or yellow? Excellent, it's yellow. Yay, well done, guys. So remember, it's chloro, bromo, CBRI, white, cream, and yellow. Okay, now what is my simplest ionic equation going to be? So these precipitates that we're forming, these are silver halide precipitates. Okay, so basically what we formed with iodide is we have formed silver iodide, right? So silver is Ag and iodide is I. So that's my product, okay? That is what is this yellow precipitate. But they're asking me, how did I get that? So what is my ionic equation going to be? So basically, guys, so a bit of confusion here, but the correct answer, the simplest ionic equation is basically just Ag plus I minus gives me AgI, yeah? So this is Ag, these are both aqueous, and this is a solid precipitate. You don't need to write NO3 nitrate because that is not the simplest ionic equation. Those are all spectator ions. So whatever one they give you, okay, it's the same thing. If it was silver bromide, okay, which forms a cream precipitate, it's this. And if it's silver chloride, which forms a white precipitate, it's this, okay? So it's just the silver plus the halide ion giving you that solid precipitate. Okay, use your knowledge of the reactions of halide ions with silver nitrate to suggest why the student did not include 1-fluorobutane in this experiment. Okay, why did he do that? Exactly. So you guys are saying because it's not reactive enough, or it would require too much energy to break the bonds, it reacts very slowly. Exactly. So this is because you can just say 1-fluorobutane is got high bond enthalpy, therefore unreactive with silver nitrate. So that's why they didn't put it in. And yeah, that is the last question. Okay, guys, so it's just past 12 o'clock. So what we'll do is we'll go for a lunch break now till 1, and then we will continue talking about elimination reactions of haloalkanes and also haloalkanes in the ozone layer and all of that. So enjoy your lunch. If you've got any questions, please feel free to leave them in the chat and I will address them in the break. But otherwise, I'll see you guys back at 1. Hi everyone, welcome back. So I hope you enjoyed your lunch break. So we are going to be moving on to talking about different reactions with haloalkanes that you need to know about. So we have already covered the substitution reactions with haloalkanes. But there are also other reactions that haloalkanes take place with, and these are elimination reactions. So essentially, what can happen is that when we are eliminating something, i.e. we are getting rid of it, okay, so this is in stark contrast to substitution reactions where we are swapping in the elements and into the organic compound. So what you can see very nicely happening over here is this is bromoethane. Okay, there are 2 carbons, and this is a bromine. And essentially what has happened is that I have reacted it with potassium hydroxide. Okay, and interestingly, what has happened is that usually what you might predict and what we have seen before is that the OH will swap with the Br, right? That is basically what we have seen in our nucleophilic substitution reactions. But what has actually happened in this case is that because of the conditions of this reaction, this OH, rather than coming over here and attacking it like so, and then having this bond being broken like we've seen before, it does something else. And instead, the properties of this potassium hydroxide is that it totally gets rid of the Br and it removes it from the equation. So it removes the Br and it removes the H, and what you can see happening is that instead we end up with an alkene, okay, and basically we end up with ethene, and the Br comes out of this out of the compound, and we get potassium bromide, and we get water forming. Okay, so why does this happen? This is quite unusual, and this is quite unique. So because what we have seen before is that when we talked about the nucleophilic substitution, okay, where there was a swap and the haloalkane became an alcohol, the hydroxide that we used, that was dissolved in water. Okay, and that is why that reaction was happening, and we had a nucleophilic substitution. When we have this elimination reaction, again, we are using an OH, okay? We still have got an OH. Even in the nucleophilic substitution, we had an OH. Even in the elimination reaction, we have got an OH. But basically, this potassium hydroxide is actually dissolved in ethanol. Okay, it's not dissolved in water. And basically, because it's now dissolved in alcohol, it sort of changes the conditions and the way in which the OH reacts, and instead it undergoes an elimination reaction. So you have to be very careful, and as we will see, you need to read the question and see what the reaction conditions are, okay? Because if this potassium hydroxide is dissolved in water, okay, if it's dissolved in water, basically what will happen is you will get your typical substitution, and you will instead get an OH over here like we've seen, and it will swap over. But when there is no water and this is dissolved in ethanol, okay, you get this elimination reaction. So this is the reaction that we're going to talk about now. So as I've said, haloalkanes, yes, they do nucleophilic substitution, but they also do elimination reaction. So now, elimination reactions, they still involve a hydroxide, but this hydroxide, it can be sodium or potassium, whatever, that is irrelevant, but the hydroxide is dissolved in ethanol. Okay, and ethanol is an alcohol, which I know makes it even more confusing, but the properties of the ethanol are such that it makes the hydroxide, it makes it a base, and it goes into an elimination reaction. So don't worry about the details, but the key thing to remember is that there is no water present. If there is water, okay, you get a substitution reaction, and the whole reaction changes. So you basically heat up the reaction. So let's just say, for example, we have bromomethane. Oh, it won't work with methane. So let me just do bromopropane. And we heat this mixture up, okay, and we dissolve it with potassium hydroxide, okay, and we dissolve this potassium hydroxide in ethanol, and we add heat. Okay, so these are the conditions for the reaction to take place. Okay, and essentially what ends up happening is that we get an elimination reaction, and I will show you guys the reaction mechanism, but just for an overview, what is happening is that where this haloalkane bond is, okay, where the bromine is, you basically, with that carbon, it's being taken away and you get a double bond being formed. So this bromine goes away, okay, and instead what happens is that you get a CC double bond over here, okay, and one of these hydrogens will be removed, and I will show you guys how that happens. And the product that you would get is ethene, or in this case, you would get propene. And this is a very useful reaction because you will know that alkenes are very much used in polymers, they're used in plastics, and sometimes in fuels. So in the industry, this reaction is very beneficial for us. So this is why we do it. And we've got a question which says, why are the products alkenes and not alkanes? So this is just the way that the reaction takes place. It's an elimination reaction, and it basically eliminates that part of the, because it takes away a Br and a H, it means that you're left with a double bond. So that's why it becomes an alkene. And just so you guys are completely clear, remember alkene are compounds with double bonds, and alkanes are single bonds only. Yeah. Okay, so we're just going to talk about the reaction mechanism now. So let me just draw this out very clearly for you guys, and you can just draw this along with me as well. Okay, this is bromoethane, and this is a primary haloalkane. Okay, now essentially what happens is that I get an OH. Okay, again, this is a nucleophile, but what has happened is that this OH is dissolved in ethanol. Okay, this ion is dissolved in ethanol. It's not in water, it's in ethanol. Okay, and ethanol has totally changed the game, and it now reacts very differently. Okay, so basically what happens is that we said earlier that the this carbon and this bromine bond is got a difference in polarity, right? Now, interestingly, what happens is that the CH bond also, it's got a very slight difference in polarity. It's not the same as the level of the CBr bond, but there is a very small difference in polarity between the carbon and the hydrogen. And what that means is that this OH is slightly attracted to this hydrogen. So this is very weak, okay, but this hydrogen is actually very slightly positive. We normally don't even denote it on the normally we don't denote it because it's a very slight positive charge. But essentially what happens is that the OH is attracted to this hydrogen, okay, when it's dissolved in ethanol. So we can just get rid of that. It's just for us to know that's slightly positive. So this OH gets attracted to this hydrogen, okay? And now because this H and this OH are attracted together, essentially what happens is that these have kind of reacted with each other to form water. So what then happens is that the electron pair that was from this CH, okay, this electron pair will actually move over to this bond. Okay, so I know that sounds really confusing, but basically what has happened is that this hydrogen is very slightly positive in relation to carbon, really, really slightly. And because this OH has got an electron pair, it likes this hydrogen and it will react with it to form water. Okay, now because this hydrogen is taken away from here and it's slightly positive, the electron pair that was in this bond actually comes to this CC. Okay, the electrons get transferred from this CC. Now, because the electron pairs have been transferred here, what happens is that that single CC bond, okay, it becomes a double bond. Okay, because it has now got an extra pair of electrons. So instead of it being single, it becomes a double bond. And basically, then what happens is that the bromine will then take the pair of electrons in the CBr bond, and it therefore leaves a bromide ion. So because there was a difference in polarity between these two, the electrons that are here, they go to the bromine. It's sort of just like a stepwise pathway, and this pushes it out, and the bromine gets removed from this equation, okay, and we then form a bromide ion, okay, because it has taken the electrons. So we've got a question which says, why is the OH not attracted to the carbon? So this is just basically the property of it when it gets dissolved in ethanol. When we dissolve the hydroxide ions in ethanol, it just behaves very differently, and it's what's called basic. It becomes basic, and it's more attracted to this hydrogen to form water. That's just a property of it. Whereas if it wasn't dissolved in ethanol, we would have the reaction pathway that we've seen before. And we've got a question which says, why does the hydroxide ion go up to this one and not this one? This is just for ease of drawing. I mean, I could draw it over here as well and then show you the arrows like this, but it's just for clarity. We've just put it up there, but that doesn't really matter. Okay, so just to finish this off, so basically what has happened is that we have taken away, I know this is a bit tricky. So we have basically taken away this hydrogen. Okay, this hydrogen has gone from here and it has bound to this H2O. So basically you form a H2O because this has come here. This Br is also taken away. It's over here. Okay, so what you will see that you are left with is that you are only left with 2 hydrogens on this carbon. So I've got one H and one H. And this hydrogen has gone, so I'm only left with 2 hydrogens on here. So that is a H and that is a H. So carbon can only form 4 bonds. So this makes sense, right? So that's why I have got ethene been formed over here. Okay, so this hopefully makes sense to you guys. So this is just the reaction mechanism. So we just talk about this again in a bit more detail. So as we've said, the OH ion, okay, this is electron rich, okay, and it's got a lone pair, and it forms a bond with one of the hydrogen atoms on the carbon next to the CBr bond. This is just a property of it. So this OH, it likes the hydrogen that is next to the CBr bond, because basically there is a lot of difference in electronegativity, and it causes a bit of a shift where this is slightly positive. So either you can draw on this one or you can draw on this one, but this OH, it does not attract, it doesn't come to this hydrogen because there is a Br here and there is a difference in polarity. So I don't want you guys to get confused, but it's just to understand that it's the one adjacent to it, it's next to it, okay? So this hydrogen atom, as I said, is very slightly positive, but it's so slight that you never really write the slightly positive at the top. You just don't do that. So this OH is attracted to this hydrogen. Okay, what then happens is that the electron pair from the CH bond now becomes part of the carbon-carbon double bond. So because this then took these away, there were electrons over here, which then moved to this. Okay, so this is now gone. We can cross that off. The electrons that were still over here, they went here, and this therefore became a double bond. Now, for this to become a double bond, obviously we can't have all of these these can't be here as well, because there are 5 bonds. So this bromine then breaks off because there are extra electrons here that have come from here. These get passed on to the bromine, and the bromine takes the pair of electrons in the CBr bond, and that leaves us with a bromide ion. Okay, so from this equation, we have got H2O, which is over here. Okay, so this is then gone. and we formed a bromide ion over here. That's formed, so this is gone. And we got a double bond because of that extra pair of electrons that came here. This is my double bond here. And then I've got 1, 2 hydrogens here, 1, 2, and 2 hydrogens over here. So does anyone have any questions on that pathway? Because I know it's a little bit harder than nucleophilic substitution. Okay, so we'll just have a look at another example here now. So obviously this can happen with any haloalkane. So what we will see here is, so here we can see we've got 1 bromopropane, and this is potassium hydroxide, and this is dissolved in ethanol. Okay, so we dissolve this in ethanol, and remember, because it's in ethanol, we will now have an elimination reaction. So we can see our products. So they've shown us nicely here that actually what happens is that we get a double bond being formed here, and we get potassium bromide from this K, and we get water. So what I want you guys to do is to just have a go at drawing out the reaction mechanism over here on what's happening. So let's just say that I put for you guys here an OH here. So if you guys can just have a go at drawing the arrows and showing the movement of the bonds. Okay, so hopefully you guys have had a bit of time to do that. If you had no idea where to begin or you're really confused, don't worry. This is tricky if you've not seen it before. So we just go through the basic principles again. So remember I said that this CBr bond, there is a significant difference in polarity between these two, and the hydrogen that is adjacent to this bond, i.e. next to it over here, is kind of affected by it, and the hydrogen is slightly positive. Okay, so this hydrogen is slightly positive. We've got a hydroxide ion, which we put in ethanol, which makes it more likely to take place in an elimination reaction. So basically, this is slightly positive. So these lone pair of electrons are attracted to this hydrogen over here. Okay, that is the first arrow that we want to draw. Now, because these electrons from the OH have come to the hydrogen, okay, these have formed a bond together and these two are very happy, okay, so, and that is where we got our H2O from. So we can forget about this H now, it's gone away, but there is a shared pair of electrons between these two. What happens to those? Well, that shared pair of electrons, it gets transferred to this CC bond over here. Okay, so there is an extra pair of electrons between these two carbons, and that generates this double bond over here. Okay, so we've got that double bond, but remember we've now got that there would be 5 bonds on this. So this bromide, there is a difference in polarity, and this bromide wants to get out of this compound now. So the pair of electrons that is between this carbon and this bromide, the pair of electrons, by heterolytic fission, it will go to the Br. Okay, and it's just kind of like a ladder, and it's literally just the 3 arrows. The more you do, you like won't even have to think about it. I can just do it without thinking because I know that it goes 1, 2, and 3. And the more that you practice, it's actually it just comes intuitively. So this then goes over here, okay, and we form Br minus. Okay, now because this is a full word equation, the potassium has reacted with the Br, giving us potassium bromide, but it's a bromide ion that we have. And we've just got a question which says, does it matter which side you put the arrow in the CBR? So no, that sort of thing doesn't matter. The only thing with curly arrows that matters is showing where it's going from and where it's to. If you like put it like this, okay, if you just think about it logically, it's the same thing, isn't it? You're going from this bond to this BR, so it doesn't matter where you draw it. It's just about, it doesn't matter which side you do it on, it's just as long as it shows the same thing. Okay, and are you not going to draw the K plus? So the K plus is not actually taking part in this reaction. So basically, guys, what's happening is that this is a K plus and this is a OH minus. Okay, so this OH minus is going over here. This K plus is just sitting in the solution, and it then reacts with the Br minus, okay, to form KBr. So we don't need to write out the K plus. It's what we call a spectator ion. It's just watching what's happening. It's not taking part in the reaction. It's just there to react with the hydroxide, because you don't, in solutions, like when you do chemistry experiments at school, you don't just have OH sitting on its own. It's always bound to something like potassium hydroxide, sodium hydroxide, magnesium hydroxide. That's how it exists in a solution. But these are metals that don't take part in the reaction. So hopefully that makes sense, guys. So well done. I know that's really quite tricky. So just to recap that, so basically when we talk about haloalkanes, so this is just an overview. When we talk about haloalkanes, okay, there are 2 types of reactions that I want you guys to know about. Number 1 is nucleophilic substitution. And this is what we did in the morning, yeah? So nucleophilic substitution. And the other one, which we have just talked about, is elimination. So as long as you've got an overview and clear differences, that's fine. The details we can fill in later. So when we're talking about this one now, nucleophilic substitution, when we put this in, we put hydroxide ions with the haloalkanes. Okay, these are in water. This is aqueous hydroxide ions. So the conditions are very important for both of these. Okay, both of these, we are reacting them with hydroxide. So technically the same thing should happen. Okay, they're both reacting with OH, but the key difference is that with nucleophilic substitution, the hydroxide is in water. We dissolve it in water. In elimination, we put it in an alcohol. So basically, this is a so what happens, so we're talking about nucleophilic substitution, and what happens is that our haloalkane becomes an alcohol. Okay, so we can see that very nicely over here. So this was 1 bromopropane. Okay, so just to go back, guys, we saw 1 bromopropane here, and here it became propene. This is elimination. Here we've got 1 bromopropane, and it became propanol. So this Br swapped with this OH. This is a substitution reaction. It's a swap, right? It's just like when you get a substitute teacher. They just moved spaces. Why did this happen? So again, I'm just going to draw this out. I know you guys know this, but we'll just go through this very briefly again. There is a difference in polarity between the slightly positive carbon and slightly negative bromine. The electrons are attracted to this carbon, okay, and this bond therefore breaks by heterolytic fission, yeah? And then remember, we get a COH and we get the bromide ion here, and it's reacted with potassium. So that is substitution. Now, the reagent, i.e. what we react it with, the reactants, not the reactant, sorry, what you react it with, what's present is potassium or sodium hydroxide. Yeah, it can be any hydroxide. Now, the condition is that it is an aqueous solution. It is dissolved in water. If you don't dissolve this in water and you start putting alcohol or something else, you will not get a substitution, you will get another reaction. Okay, so that's why the conditions are really important. So this is an aqueous solution and you heat it under reflux. Okay, so that is nucleophilic substitution, and that was the first reaction that we talked about. But we've also said, okay, that it takes part in elimination reactions. So what happens in an elimination reaction? Well, that is if the hydroxide ions are dissolved in alcohol. Okay, so we take those OH minus ions and we put them in alcohol. And basically what happens then is we start off with our nice haloalkane. Okay, we've got a CBr, and instead it becomes an alkene. Okay, so here our change in functional group was haloalkane to alcohol. Here we are going from haloalkane to alkene. Okay, and this is just purely because we dissolved it in alcohol. This is the property of it. Okay, so again, we can see that this reaction taking place over here. So I will just show you guys that we take this OH. Okay, there is a very minor, slightly positive charge over here, which is attracted to this hydrogen. Okay, this then goes on to form water. The pair of electrons that are here will then go to this double bond because they no longer are, the hydrogen has now gone, and this carbon CBr bond will then break. Okay, so this one looks slightly different basically because they wrote the Br up here, so it looks a bit weird, but it's the same thing. Like if the Br was at the bottom, then you just draw it here. And yeah, so this Br then disappears, and this hydrogen then disappears with this OH. So you're left with ethene and potassium bromide and water. Okay, so the reagents, again, we are using potassium or sodium hydroxide. It's the same thing, but the key difference is that this is in ethanol. Okay, so we dissolved it in alcohol and we heated it up. And both of the bond fissions that are being broken, both times the CBr bond that is being broken is by heterolytic fission. Okay, so this CBr bond is heterolytic because heterolytic is always when the it's uneven. Okay, hetero means different, so that the pair of electrons are just going to one species, and that is heterolytic fission. Okay, and this mechanism we call it elimination. So, okay guys, so note the importance of the solvent to the type of reaction here. If you want a substitution reaction and you want your CBr to become a COH, okay, you need to dissolve your OH, you need to dissolve it in water. If you want your CBr to somehow become a CC bond and you want to make an alkene, you need to dissolve it in alcohol, okay? And that is basically the key differences between them. And we've just got a question which says, do we lose a mark if we just say alcohol, or do we need to say ethanol? I would just specifically say ethanol for the purposes of your exam, but it's any alcoholic solution. Okay, so let's just have a look at a question now. So haloalkanes are used in the synthesis of other organic compounds. Okay, that's nice. So hot, concentrated, ethanolic, potassium hydroxide. So guys, this is where we don't just whiz through the question stem. We need to read it very clearly, okay, and carefully. So ethanolic potassium hydroxide reacts with 2-bromo 3-methylbutane to form 2 alkenes that are structural isomers of each other. The major product is 2-methylbutene. Name and outline a mechanism for the conversion of 2-bromo 3-methylbutane into 2-methylbutene according to this equation. Okay, so they've given us the equation, which is nice, so you don't need to work it all out. So what is our name of our mechanism, guys? Exactly. So we don't normally you can say nucleophilic elimination, or you can just say elimination. The mark scheme has just got elimination down, and I think usually we just say elimination. Okay, so our mechanism is elimination. Excellent. Okay, so let's have a go at now drawing out our mechanism. So they've given you, like, this compound looks really complicated, and like you might be thinking, how do I even draw this? So don't panic. Okay, all you need to do is just look at where the functional group is. Okay, you just look at where the BR is and where the C is, because this is where all the action is happening. So don't worry about how you'll draw out the rest of this. Just focus on where the BR. So just have a go at drawing that out, and I will show you guys how to do it. Okay, so I'll just help you guys out, because this is actually quite a hard one to draw. The next question is a little bit easier. So let's just go through this. So if any of you guys struggled to draw this one, what I would do is, they're asking for the mechanism about bromine. So I would just try and I would just put my bromine is here. Okay, and I know that bromine is bound to a carbon over here. Okay, and I know that there is a hydrogen. Okay, so this is my CHBr. This is basically, this bit is what I've drawn. I know that this carbon is also bound to a CH3. That comes over here. And then I know that this carbon is attached to another carbon, which is a C here. That's this C. Okay, and then there are two methyl groups. So there's one methyl group here, HC3, and there's one methyl group here, CH3, and then there's a H. Okay, so it's a bit tricky to draw this out, but this is just a structural formula, and this is a displayed formula. And don't worry, if you put the BR up here or you put the BR down here, it doesn't matter. It's just that's really irrelevant. Okay, don't worry about if you put it up here or down here. Okay, so basically that is our structure, and we know that it reacts with OH minus. Okay, so basically what is happening is that our OH minus, I'm just going to draw it here, because we know that the OH minus is attracted to the hydrogen that is adjacent to the bromine, right? So if my bromine is here, it's the hydrogen that's next to it. So basically this OH is attracted to this hydrogen, okay? And these two go along together and they form water. The pair of electrons that is between these two gets passed up to this C double bond. And meanwhile, because there is an extra pair of electrons here and there is a difference in polarity between these two, this CBr bond breaks and the electrons go to bromide, forming a bromide ion. Okay, so therefore I will then be left with essentially something that looks like this. Okay, so I've got my CC double bond here. This hydrogen has gone, and I'm just left with two methyl groups. So I've just got a H3C and a H3C here. This bromide has gone, so I'll have a H, and I'll have a CH3. Okay, and then other things that I will be left with are, obviously I had an OH and a H, so I'll get a H2O, and I formed a bromide ion. Okay, so I got a Br minus. And that is basically my mechanism. So if you guys got even half of this right, that is really excellent, because I know this is quite hard to understand. First off, does anyone have any questions, or did you guys like put your H somewhere else and you're a bit confused about how you would draw it out? Please just feel free to ask. So will water be present in all elimination reactions? So elimination reaction is basically when you get rid of something. So if there is a OH, then yes, you will form H2O, but obviously if it wasn't involving OH, then you wouldn't. What's the difference between writing H3C and CH3? So you have to write H3C because this line is showing where the bond is between. So it's just very good practice, because if you write C, you can write CH3 like this, but it's part of the IUPAC, the Universal Naming System. This is very messy. We don't write it like this. You want to show that the C is bound to a C, and it's attached to 3 hydrogens like so. So it's very good practice to write C and then H3C like this. It's the same thing, but it shows that there is a bond between these two. This is very messy, and it's not typically written out like this in textbooks. Okay, great. So I think we will move on from that one. So well done, guys, if you managed to get any part of that correct. So that is just the answer there. And guys, you can see that basically they did theirs upside down to me. So their H was at the top and their BR was here, but like my H was at the bottom here. But see, it doesn't matter. But if you do it at the top, it just forms this ladder, which is actually really easy to memorize. Okay, but anyway, so okay, let's just do one more of these. So I think this is a really similar question. So consider the following reaction. Okay, actually this is different. So name and outline a mechanism for this reaction. So guys, what mechanism is this one? Exactly. So guys, this one is nucleophilic substitution. This one is not an elimination reaction. Well done to those of you who changed your minds. So this is a substitution. So just look carefully. Here's my halogen, and I had a hydroxide. All of a sudden, I've now got an OH over here. Okay, it's a swap, isn't it? So it's a substitution. And the mechanism, we can quickly do this one together. You guys are probably pros at doing this now. So for this mechanism, I'll just give you guys 30 seconds to do it, and then I'll show you how to do it. So great. So in this case, again, I've got my OH over here. This is slightly positive. This is slightly negative. My OH is attracted to this carbon, and this CBr bond breaks. Okay, forming a bromide ion, which is shown with the potassium. Okay, so I think we've seen a few of these. Okay, so we'll just quickly do this one. I know it's a bit tedious to keep drawing these out, so I'll just show you guys this one. So an alternative reaction can occur between this haloalkane and potassium hydroxide, shown by the following equation. So now they've shown us an elimination reaction, okay, and we've done the mechanism for it. So the question is saying, give one condition needed to favor the reaction shown in part B than in part A. So what do we need for it to have elimination rather than the substitution reaction over here? Excellent. So the correct answer is that it should be, so you can say alcoholic or you can say ethanolic, either is fine. And you should, that's basically the correct answer. You can say high concentration of your potassium hydroxide, but really you should be saying that you need alcohol or you need ethanol present. Okay, great, well done guys. So we're just going to do a quick quiz now on what we've covered. Well done guys. So this one is primary because the carbon it's attached to is 2 hydrogens. Okay, so this one is 2 bromo, so it's, well, let's have a look. Oh, I think the correct answer to this one is 2 bromo, 1 iodopropane. Yep, that is the correct answer. Excellent, well done. So haloalkane to an alcohol, you want it aqueous, you just want it dissolved in water. Exactly, so you have to dissolve the potassium hydroxide in alcohol or ethanol if you want to make it into an alkene. Excellent, well done, everyone got that right, that's great. So reacting a haloalkane with potassium hydroxide aqueous, so whenever something is aqueous, that means it's dissolved in water, okay? So you don't need to specifically write dissolved in water as long as it says aqueous. So you will get an alcohol, yeah? You'll get a substitution reaction. If this was an ethanol, you would get an alkene, okay? Great, well done guys. So that's excellent. So we'll just go for a quick 15-minute break. So if you guys come back at 2, and we will continue on our last session about ozone layer and organohalogen compounds. And just leave any questions in the chat. Otherwise, enjoy your break and see you back at 2. Hi everyone, welcome back. So I hope you guys had a good break. So we're just going to move on to the last and final section of today, which is talking about how halogenalkanes are formed and their impact on the environment. Okay, so let's go straight into it. So we've talked about the reactions that halogenalkanes or haloalkanes, they both mean the same thing, by the way. Sometimes we call them halogenalkanes or haloalkanes for short. And we've talked about what reactions they undergo, and quite commonly these can be substitution or these can be elimination, but we haven't really talked about how they actually arise and how we make them. So it's actually then they don't actually get made on their own, and they are a compound that is created under a lot of pressure, and they require very specific conditions. So if you've just got, for example, you've got some Cl2 and you've got methane, if you just try and mix them together to make chloromethane, it won't work. Okay, they won't react together. You need some very specific conditions, and the main thing that you actually need is UV light. Okay, without UV light, these will not react with each other, and they need the UV light as a source of energy, and it kickstarts off the reaction. So when you put a mixture of an alkane and a halogen into bright sunlight, okay, the alkane and the halogen will react, and you will form a halogenoalkane or a haloalkane. And specifically, it is the UV component of the light that starts off that reaction. Okay, because as I said, if you just take methane and chlorine, they will not do anything with each other. You must have UV light. Okay, and we can see that here this is methane, chlorine, and we get chloromethane being formed. And because one of the H's are being removed from the methane, we get some HCl. So this is not actually a balanced equation, it should be Cl2. So hopefully that makes sense. I'll just quickly draw it out. So we've got CH4 over here, methane is CH4 plus Cl2. Okay, and essentially what happens is in the presence of UV light, this bond breaks, and this Cl and this CH bond breaks, and instead we get a CCl over here. So we get, and that H then combines with this leftover Cl. Okay, so we get hydrogen chloride and chloromethane. Okay, so this reaction that takes place, it doesn't just happen in one go like that. The way that this takes place is actually in 3 stages, which we will talk about. It's known as a chain reaction. So, and just to compound that, so as we said, alkanes, they do not react with halogens in the dark and at room temperature. Okay, you must have sunlight, and in particular, it is the UV radiation that kicks off this whole process. Okay, so this reaction, this overview that is we have seen over here, okay, this is known as something called free radical substitution. Okay, if you've not heard of this term before, don't worry, it's actually very self-explanatory. I'll tell you guys what a radical means, but this is again a substitution reaction. And it basically starts off a chain reaction, and we get 3 stages. So in order to convert that for that CH4 to react with that HCl, okay, and to form our chloromethane, this overall process requires 3 stages, okay? And initiation is the first thing, i.e. to start it off. And you need UV light to kick this off. We then have something called propagation, which is like the in-between step, and it kind of just spurs it forward to keep on generating this reaction. And then we have termination, which is the end, okay? So these steps and this free radical substitution, this applies for the reaction between any alkane and any halogen. Okay, it doesn't matter what you get. You can put bromine, and you can put pentane together, or you can put iodine, and you can put butane. Okay, it doesn't matter. The principle stays the same, that when you react a halogen with an alkane, okay, it's known as free radical substitution. And this process requires 3 stages. It doesn't just happen on its own. Even though we show it as one here, this is actually a 3-step process. Okay, so we're just going to go through each of these steps now. Okay, so the first one is initiation. So we'll just keep our simple reaction at the top, so we know what we're doing. Okay, we've got alkane and we've got a halogen. Okay, and we are trying to make a haloalkane in the process. Okay, this is our overall reaction. Now, what are we going to do to start this off? So the first step of this reaction is basically breaking this Cl-Cl bond to form 2 chlorine atoms. Okay, because until we break this bond, we need 1 Cl to come over here, right? If we do not break this bond, nothing is going to happen. It will just sit on its own. Now, where do we get the energy to break this Cl-Cl bond? Well, as we said, that comes from UV light. Okay, so energy from the sunlight is absorbed by this chlorine to allow this bond to break. So the energy of the UV light is greater than the this should say Cl-Cl bond energy. So the bond breaks, because obviously UV light is very strong, so it can easily break these chlorine radicals, the chlorine compound. Now, basically, what happens is remember earlier I talked to you guys about homolytic and heterolytic fission, right? So we said that heterolytic was like if we've got a CCl bond, basically both of the electrons go to the CCl and we get a Cl minus charge, right? That was heterolytic fission. Now, because these are both chlorines and because these are both the same, okay, they split differently, and they split such that one electron will say I'm going here and the other one will go here. So each chlorine atom has now got 1 unpaired electron, and we show this with a dot. Okay, it's got 1 unpaired electron, and this is known as a radical. Okay, it's a free radical. Okay, and this process by which it has split is no longer heterolytic, this is homolytic. So in the substitution reactions and the elimination reactions, we were seeing heterolytic, but when we're actually making these haloalkanes, we utilize homolytic fission. Okay, so since both of the atoms are the same, the CCl bond will break homolytically. Okay, that is 1 electron going to each chlorine atom. Okay, so as I said, we've got a Cl and a Cl, 1 goes here and 1 goes here, and therefore this results in 2 separate chlorine atoms which have both got this dot in front, and whenever you see this dot, it means it's a free radical. So this is very different. So I don't want you guys to be thinking of Cl minus, okay, this is a negative charge, this is an ion, and it's got an extra electron, okay? This radical is totally different. This is an unpaired electron because the bond has split homolytically. So it's totally different. And these free radicals, they're very interesting. They're highly reactive, more so than any ion, and they really are looking for the chance to just bind to anything. And this is what actually makes them very dangerous in the atmosphere, okay, because they are highly reactive. And this is what we call initiation. Okay, this is the first step in order to help me make my chloromethane, okay, for me to make it. The first step is I get some Cl2 and I basically break it into 2. Okay, so this is my reaction step. So this is initiation. So I've got Cl-Cl and I get 2 chlorine radicals, or you can write as I've done. You can do it like this. Okay, so that is initiation. Now, we then move on to propagation. Okay, so essentially what's happened is that I kickstarted off my reaction and I've got these free radicals that are roaming about. Okay, now these are highly reactive. So I started off with methane and I had Cl2, right? This is what was in my reaction mixture. Now I broke up that Cl2 to form these radicals. These radicals are very unstable, okay, and they want to try and react with something and get their stability back. So what the chlorine free radical does, okay, is it takes a hydrogen atom from the methane to form hydrogen chloride. Okay, so basically what is happening is that the Cl radical, okay, it sees that methane and it thinks, let me try and react with this methane instead, okay? And basically what it does is, you can just imagine that if I have got a Cl radical here and a CH4, basically what it does is it sort of pushes one of the hydrogens out the way, okay, pushes the hydrogens out the way and it forms HCl, but we're left with CH3, okay, and I then get a CH3 radical. Okay, so does this make sense, guys? So what is basically happening is this radical, this is really unstable, okay, and it is pushing, it wants to try and sort of stir up this methane. So it approaches the methane and it takes one hydrogen away and we form hydrogen chloride. This is stable, okay, and this is fine, but we still had this unpaired electron, okay, and this is highly reactive. Okay, so what this does is that it moves this radical to the CH3, so we therefore get a CH3 free radical. Okay, this is another radical again, and this is unstable. Okay, now essentially this HCl is fine, this is already reacted. Okay, so just remember, going back, our initial reaction was CH4 plus Cl2. Overall we get CH3Cl plus HCl, right? So what we've done so far is, in our first step of propagation, we've made this HCl, so we're fine, but somehow we haven't made this yet. Okay, so what then goes on to happen, okay, is that this CH3 radical that is very unstable, what it does is it goes back again and it wants to react with something. It wants to get rid of this charge. It sees some more Cl2 that's sitting in the reaction mixture, and it thinks, you know what, I'm going to react with this Cl2 again. Okay, and basically what that will do is that will then just propagate. It's called propagation because it keeps pushing things forward. And what that will do is it will bind to one Cl. So you'll get CH3Cl, okay, which is stable. But what happens is that it releases another chlorine radical, okay, and it basically pushes that radical, it basically reforms this radical. So what you guys can see is this is just, I'm just showing you two reactions. There are millions of these happening at the same time because of this free radical process. It's highly unstable and it keeps propagating the mixture and pushing it forward. Okay, so essentially you make millions of these chlorine radicals and they are highly reactive. And again, this chlorine will then go back to the CH4 and it will make more of this. And these will just keep happening over and over again. Okay, so that is propagation. So this is already just shown here, so that's fine. So I don't want to lose the momentum. So we've basically got these free radicals, CH3 and Cl. Now, how do we basically stop this from happening? Okay, because this is happening at a lot of speed and there are a lot of radicals being produced. Okay, so the only way that we can stop it is if we can get rid of the free radicals. Okay, so termination is the only way in which we can get rid of that Cl, or we can get rid of that CH3. Okay, and sorry, it doesn't matter where you put the dot, by the way. It doesn't matter. So the only way that we can get rid of these radicals is if they react with each other. So what we can do is we can make the Cl react with the Cl. Okay, and we can form Cl2. Or we can make this CH3 react with this CH3, and we can make C2H6, okay, and we can make ethane. Or what we can do is we can make this Cl react with this CH3. So these are just different options of what we can allow to happen, and then we will get CH3Cl, and this is what we wanted to make. Okay, this was our chloromethane. Okay, so these are as of what I've just drawn. So in each case, two free radicals react to form a stable compound with no unpaired electrons, and that is the only way that the reaction will end. Okay. Does anyone have any questions on that? So I just want to just go through that one again. So it's a little bit tricky, but basically we've got initiation. Initiation, the key thing to remember is that we need UV light. Okay, so you guys can just write this along with me so that it sticks. So in initiation, what I want you guys to remember is that we have homolytic fission. Okay, so we get a Cl2 and you put it in some bright sunlight and it breaks up. It forms these radicals. Okay, and that is basically initiation. That's it. That is all that's happening. Okay, then what happens is these Cl radicals, as I said, they are very, very unstable, okay, and they cause a lot of damage. So what they do is we then go to propagation. You can just think of propagation as pushing, and the reaction is happening very, very quickly in multiple steps. So this Cl radical, okay, it sees methane and it wants to react with it, okay? Now this unpaired electron, it's not just going to disappear because this has got no charge, so something has to have an unpaired electron over here. Okay, so basically what happens is one hydrogen can come out. Sorry, this should be CH4, sorry, this is methane. So I've got one Cl that has come, one hydrogen that has come out, and again, I form a CH3 radical. Okay, this radical again is very, very unstable, and it goes and hits another Cl2. And basically, again, another Cl can one Cl can come out, so I can get CH3Cl, but I'm left with another free radical here. If you're getting mixed up about where did I get this dot from and how does it get moved, basically the radical just gets moved to the thing that it reacts with. So the radical moved from this chlorine to the CH4, and then obviously one hydrogen had to come out. Here the radical moved to the Cl2, and then one Cl comes out because the unpaired electron comes there instead. So you just move one onto the other side. So can you guys see that? So I form an unpaired electron of Cl, and here it's of CH3. Okay, this process happens like a million times. Okay, this is a very simplistic overview, but this keeps happening and it keeps taking Cl from the initial reaction mixture. This will keep going on indefinitely until we terminate it. Okay, so this is known as termination and it stops. The only way that I can terminate the reaction is to have the unpaired radicals reacting. Okay, so I have to get this CH3 and I will say, okay, react with another CH3 to give me C2H6 because now the charges will cancel out, okay, because I've got two unpaired. Or I can take two of the Cls and I can make Cl2. Or I can take one CH3 plus a Cl and this will give me CH3Cl. Okay, and the majority of the product that's formed here is CH3Cl, which is chloromethane. And that is basically what we are trying to form in this whole process, which was a halogenoalkane. Okay, guys, any questions on that? Does it matter which side you put the radical? No, it doesn't actually. Some notations they put it at the end and some they put it in the front, and that doesn't matter. Okay, so let's just have a look at some questions then. Okay, so we can look at it with bromine instead. So what stage of a free radical substitution of bromine with methane is represented by the following? All right, guys, is this initiation, is it propagation, or is it termination? What do you guys think? Fantastic. So this one is actually termination, guys. So this is a bit of a trick. It's not initiation because the free radicals are joining together to form a stable compound. Okay, this is the opposite of initiation. This is ending the reaction and we are forming a stable compound. Okay, what is this one, guys? Excellent. So this one is propagation. Fantastic, because what you can see is that a radical is reacting with the stable compound and it is forming this free radical and it's pushing the reaction to go further. Okay, and what is this one? Fantastic. So this one is also propagation because we are still pushing the reaction mixture to go forward. Okay, we are still generating these free radicals. So this one is propagation. Okay, and last but not least, what do you guys think this one is? Excellent. So this is initiation. This is just starting it off. Okay, so we put these in the wrong order, but this is just to test you guys. So we are generating free radicals here. Okay, and this process is via homolytic fission. Okay, fantastic. Well done, guys. So I know that is quite tricky, but well done for picking it up. Okay, so why is this such a big deal? Okay, so essentially what is happening is that in our environment, okay, we have got a lot of organohalogen compounds. Okay, so these organohalogen compounds are ones that contain at least one halogen atom to a carbon chain. So we've talked about haloalkanes. Organohalogens are basically the same thing. It just means that it doesn't have to be an alkane. It can be like an alkene or literally any compound. And we actually use these organohalogens in a variety of things in daily life. So things like in general solvents, in making polymers, in like these flame fire extinguishers, and also in cleaning products. A lot of cleaning products contain these organohalogens, but these are actually quite dangerous, these products, and they are actually quite toxic. So this represents a bit of an issue. So these compounds that we are making, they're not found in nature. You know, things like carbon and methane and crude oil, these are all found naturally in our environment. But these fluoroethanes and these things that we're making, okay, they're not natural. These are artificial products, and they don't get broken down by the environment. So these will remain for millions of years, partly because that Cl radical is highly reactive, and so it's very difficult for these to be broken down by the environment, and they cause a lot of destruction to our ozone layer. So this is what I'm going to talk about now, because you need to know a little bit about it. So basically, what is happening is we have got this thing called the ozone layer, which you may have heard of, I'm sure, which is surrounding the atmosphere. Okay, it's just like around the Earth. So if this is the Earth over here, we've got like a layer on the outside. And basically what this ozone layer is doing is it's protecting us from UV radiation from the sun. Okay, so the sun has got very strong UV lighting, but we have got this stratospheric ozone in the middle, which basically protects us from UV light. Okay, now what is happening is that the ozone layer is becoming destroyed. And the reason that it's becoming destroyed is because of all of these products that are being made. So why is that a big deal? Why do we care if the ozone layer is being destroyed? Well, the UV light is really quite strong. And if we don't have the ozone layer in the middle, the UV light basically hits us and it affects us as humans. And it can lead to a lot of genetic damage to humans, and it can actually cause skin cancer, which is why I'm sure you've heard of that you should be wearing sun cream and protecting yourself from the sun because of the strong UV light, and it's also because of the depleting ozone layer which we have destroyed through human activities. Okay, so normally what is happening is this ozone is in perfect balance, and it is in sort of an equilibrium. Okay, so ozone is just described as O. Okay, it's actually a very complex compound, but we just call it O. And what happens is we'll just say there's a lot of O here. Okay, this is ozone, and when the sun hits this ozone layer, it's a lot of UV light. And this ozone layer, it basically just breaks down. Okay, so you might be thinking this is oxygen, but it's not. It's so it breaks the oxygen down from the ozone, and we basically get O2 giving us 2O. Okay, and basically what happens is that we form a steady state whereby this O2 then reacts with this O radical to give us O3. Okay, and that is ozone, and this is basically in equilibrium and it exists on its own, and it's constantly being broken down and built up, and this is not a problem. The problem comes when there are chlorine radicals and fluorine radicals that attack this ozone layer. Okay, so I will just show you guys these equations again. So as we said, ozone is continuously being formed and broken down by the action of UV radiation in the stratosphere. So stratosphere is just this main area where the ozone sits. Okay, this is our ozone layer. Now, in this steady state, basically what's happening is initially very high energy UV breaks down our ozone, our oxygen molecules, into oxygen radicals. Okay, so this oxygen is being broken down into O and O. Okay, and this is okay. Okay, this is okay. This O2 breaking down into O is okay, because what happens is that we get a steady state being set up where the O2 and the oxygen radicals are being broken down and being reformed. Okay, so I'll just show you guys that here. So the O2 then reacts with the oxygen radical and we get O3, which is basically ozone. Okay, so UV light hits O2 and it becomes O and O, but then this O goes back to react with the O2, giving us O3. Okay, and this process is happening all the time, and this is in balance and it's in harmony. So the rate of formation of ozone is the same as the rate at which it is broken down. But what has happened is that human activity, especially this production of all these chlorofluorocarbons in all of these products that we're making, has really destroyed this delicate equilibrium, and it has basically contributed to the breakdown of this ozone layer. So these chlorofluorocarbons that we've talked about, they are being sort of less and less used as we know about the damage to the ozone layer. So they used to be used in like refrigerants, air conditioning, literally everywhere they were being used, but we've sort of stopped now. And basically what we know is that these chlorofluorocarbons, it's fine if they're in the earth, okay, and it's fine if they're basically up till here, up till the stratosphere, but as soon as they get up to the stratosphere, they break down all of the oxygen and all of the ozone that is there. They break it down and they cause the depletion of that layer. And that is purely because of these chlorine radicals that we are forming. So the Cl goes and interacts with the ozone and destroys it. Okay, now the main issue is that basically these chlorofluorocarbons, they are very stable. As I said, they're very hard to break down, and they are quite they have quite a long longevity. So what that means is they stay in the ozone layer for a very long time. And it may take them many years to reach the stratosphere, but once they get there, okay, the UV radiation, it provides sufficient energy to break a carbon-halogen bond by homolytic fission and to form those radicals. So we form those chlorine radicals and it destroys them. So basically what is happening is that, I'll just show you on this diagram over here. So basically this is our Earth, okay, and this is where we are using all of our chlorofluorocarbons, and it's all fine, okay. These chemicals, they then rise, okay, and they go past the Earth and they reach what is called our stratosphere, okay, and this is where our ozone layer is. So these chlorofluorocarbons, they're fine. As soon as they get up here, okay, they're very much in access to UV light, so they break down and you form those Cl radicals that are really unreactive and unstable. Now in our ozone layer, we've got our ozone that's just doing its own thing and it's in equilibrium, okay, forming these radicals, and it's fine, it's in balance. But as soon as this chlorine radical comes into the stratosphere, it disrupts this balance and it starts to react with the ozone and it basically depletes it. So our ozone used to be this thick, but it's sort of narrowing now, okay, and the thinner it gets, it means that more UV light can come straight to the Earth and it can cause genetic damage to us. Okay, and that is basically an overview of what is going on. Okay, so so basically what is happening is that as I said, the chlorofluorocarbons, they break by homolytic fission. Yeah, so it was a Cl2 and they form those radicals. And because they are a bit more complex and they are bound to carbon, it's actually the carbon bond that breaks. So it's not just the Cl2. We actually get the CCl bond that breaks. And because it is initiated by UV light, we call this photodissociation. Photo meaning light and dissociate meaning separating. So let's say, for example, if you just take any chlorofluorocarbon, so these are quite complex. Obviously, we've just been looking at Cl2, but the ones that we use in refrigerants and in sprays and all that, they're like this. So basically what happens is that this CF2, Cl2, you give it a bit of UV light, okay, and the UV light hits it, and basically we form free radicals, okay, so we get this chlorine radical breaks down and we get another chlorine radical, okay, and we get two free radicals, and these are highly reactive, okay, and we call this photodissociation. So it doesn't matter what the compound is, like say if my compound was CBr2 Cl2, it's the same thing, okay, you hit some UV light to it and the CCl bond will break. Okay, so don't worry too much about that. It's just about understanding that we are generating free radicals in a process known as photodissociation. Now, as we've said, this chlorine radical that is formed is a very reactive intermediate, and it will basically react with an ozone molecule, breaking that ozone down into oxygen. Okay, so that ozone that was very happy as an O3, it will break it down into an O2, and then it's not ozone anymore, and it's not protective from UV light. So what happens is, okay, so we get this chlorine free radical that has come up to the stratosphere, it sees the ozone and it wants to react with it. And essentially, remember that whenever we have this, the radical sort of pushes one oxygen out the way, and we basically get ClO, and we get O2 being formed. Okay, so can you guys already see that O3 has gone to an O2. Okay, and then this ClO radical, it goes and reacts with another oxygen, okay, to form a chlorine radical and an O2. Okay, so you don't need to worry too much about what exactly is happening, because we can substitute the Cl with like another radical. But overall, essentially what is happening is that our O3 is breaking down into O2. Okay, that is essentially what is happening, and we are breaking down the ozone layer because of these radicals. And one of you guys have asked, why is it just chlorine? So in general, it's the chlorine radicals that cause the most damage, and they're the ones that we use most commonly in products. We don't usually use like bromine or iodine in these chlorofluorocarbons. It's usually just chlorine. So that's why that's the most common example. Does anyone have any questions on this ozone thing? Because I know it's a little bit confusing. The detail to which you don't really need to know these equations. Sometimes it might come up in the exam, but it's just good to understand overall what's happening and why it's happening, because they can give you like different CFC. So there's no point in learning like specific examples. Okay, great. So let's just do a quick quiz then. Excellent, that's right, it's UV light. Excellent, termination is the one missing. So let's have a look at this one. So guys, there is a chlorine that is attached to a carbon which is attached to one hydrogen. Therefore, this is a secondary haloalkane. Excellent. So this one, they tried to trick you actually by drawing it like this, but if you just rotate this image in your head, guys, if that's possible, but it's actually chloropropane. So this is carbon 1, carbon 2, and carbon 3, and there's just a methyl group on carbon 2. So if you look at this chlorine, it's attached to 2 hydrogens, so therefore it's primary. So a free radical is basically an unpaired electron. It's not a lone pair of electrons, guys, because lone pair means two. There are not two electrons. There's just one, okay, because it splits by homolytic fission. Excellent. So the correct answer in this one is termination is the blue one, because here we are not forming any free radicals. We're forming stable compounds from these two. You guys put this one, but you're still forming a Cl radical here. So this is actually an example of propagation, not termination. Excellent. Substitution is not a part of, it's known as free radical substitution, but that is not a step in it. Okay, so that's the overall thing. Excellent, that's fantastic. Well done, guys. So we're just going to end by doing a few more exam questions because I know we have covered a lot of content today. Okay, so let's just have a look at this question. Okay, so a student read the following passage on the internet. Haloalkanes contain a polar covalent bond. The carbon atom of the polar covalent bond can be attacked by nucleophiles. Nucleophilic attack enables haloalkanes to undergo substitution reactions. A nucleophilic substitution reaction occurs when a haloalkane undergoes hydrolysis, and the rate of hydrolysis of the haloalkane is influenced by the carbon-halogen bond enthalpy. Okay, so explain the meaning of each of the following terms in the information given above. Okay, so what is a nucleophile, guys? So with these types of questions, it's really tempting to just forget what they've written in this box. And I always used to make silly mistakes like that, but it's really important that you read this because it's there for a reason. Okay, so it's saying the following terms in the information given above. So you need to make sure that what you're saying is relevant to this passage. It's not just your own thing that you've memorized. So what is a nucleophile? Excellent. So a nucleophile is, I would just say, we've seen this one before, I would say it is an electron pair donor, or you can say it is a species which uses a lone pair of electrons to form a haloalkane, excellent, or to form a covalent bond. Either one is fine. Okay, I would just say electron pair donor. Okay, yeah, it's electron rich and it wants to give them away, so it's an electron pair donor. Okay, and then explain the term of substitution as applied to nucleophilic substitution in a haloalkane. Okay, what do we think? So when a halogen is replaced by a nucleophile, a halogen undergoes hydrolysis, and when an OH ion replaces a functional group. Great, so here they've given awarded marks for basically, as you guys have rightly said, so you can say replacement of the halogen by a nucleophile. Or you can say the carbon halogen bond breaks and a bond forms with the nucleophile. So I think everything that you guys have said, you would definitely get the mark for, because it says idea for. So you don't need to say the exact words. Okay, and then finally explain what is hydrolysis. So hydrolysis, as you guys have said, so remember hydro is water and lysis means breaking. So you can say splitting or breaking of molecules using water. Okay, a few of you guys have said using energy. The splitting of water using energy. You don't need energy. Okay, you're not using energy in this. You're using water. Water is the source of the energy. So you don't specifically have to say using energy. Okay, it's just using water. Okay, and finally, bond enthalpy as applied to a carbon halogen bond. Excellent. So bond enthalpy, as we know, is the energy required to break a bond. And in this, you can say, so energy required to break or to split the bond. Okay, or you can say heat energy required. Okay, and we've just got a request to do some of the harder questions. So guys, we're just going to do a longer question as well, because I know those ones are a bit more straightforward. So we'll just look at this longer question. Okay, so it says, the curly arrows model is used in reaction mechanisms to show the movement of electron pairs during chemical reactions. Choose a reaction mechanism that you have studied involving the curly arrow model. Name and describe your chosen reaction mechanism. In your answer, include an example of the reaction with the chosen mechanism, the type of bond fission that occurs, and relevant dipoles. And this is a 6-mark question. Okay, so this is actually a very nice question that really allows you to show off your knowledge. So why don't you guys have a go at doing that one? So I think for this one, I think you guys will probably pick the nucleophilic substitution. I don't know if you guys want to do the elimination one, but the mark scheme has got it for nucleophilic substitution. So if you guys pick that one, we can have a go at it. Okay, so hopefully you guys have had a bit of time to do that. So this question allows a lot of flexibility, but it's just about making sure that you get all the marks. So basically, you need to name your reaction mix. You need to name your reaction mechanism and you need to describe it. Okay, so there will be a mark for this. And it's saying you need to include an example of the reaction and the type of bond fission and the relevant dipole. So I'm going to say nucleophilic substitution. Okay, so there's one mark for just writing this down. And then there is a mark for giving an example. So for this type of question, it's important to be strategic. If you can pick any example and you're going to be drawing out the reaction mechanism, you might as well pick a really easy one that you know you won't get muddled in. So there's no point in making it like pentane or hexane. I would just keep it really simple and just say I've got, let's say, for example, bromomethane. Okay, and this reacts with and this will react with OH. So we can say, for example, sodium hydroxide. Okay, and what we will therefore form is we will form methanol. Okay, and we will get some sodium bromide as well. Okay, that is my overall reaction. So this is, I've named it, okay, and I've given an example. Then you want to just show the relevant dipoles and you need to draw this all out. Okay, so I'm just going to draw out my mechanism. So let's be very clear on this. So this OH will have a negative charge. Okay, this C is slightly positive, the Br is slightly negative. My curly arrow will show the movement of the lone pair to the carbon, and my electrons that are shared between this bond will go to the bromide. Okay, and I will therefore be left with OH plus Br minus. Okay, so you don't need to write sodium bromide when you're doing the reaction mechanism. And then the things that you need to write in addition are the CBr bond breaks by heterolytic fission. Okay, it's clearly asking you that what is the type of bond fission? And the relevant dipoles. So the dipoles we have already shown here, and we've shown the movement of the pair of electrons. And something additionally that you guys should say is, they haven't specifically asked, but you can just say that the conditions for this reaction, okay, so the conditions would be that this is the NaOH is aqueous. Okay, it is dissolved in water, and it's important that you add this in because if you put it in ethanol, remember you'll have an elimination reaction. Okay, and those are basically what you will get your marks for. So this reaction mechanism is 3 marks, and then you get 1 mark for heterolytic fission, 1 for saying nucleophilic substitution, and 1 for giving an overall summary of of you describing what reaction you have picked. Does anyone have any questions on that one, or are you guys okay? Okay, great. And we'll just do, let's just do one last fun question. Okay, let's have a look at this one. So chloropentafluoroethane is a CFC that has been used as a refrigerant. Draw its displayed formula. Okay, what do you guys think? So would there only be 2 carbons in the chain? Yes, that's right, because it is ethane. So there is, ethane means that there are 2 carbons. Okay, some of you are saying, would there be 5 hydrogens? So this one is a little bit confusing. Okay, so these CFCs, they are quite odd. So let's just go through this one. So you just break it down. So we know it's ethane. So we know there's 2 carbons, okay? And we know that this is an alkane. So there's only single bonds only. There's no double bonds or triple bonds. Okay, then we've got chloro. So we know that there is a chloro somewhere. So one of the carbons has got a chloro. Penta means 5, and the penta is in front of the fluoro. So that means that the penta is related to the fluoro. So that means that there are 5 fluorines. Okay, and it's basically like so. So 1, 2, 3, 4, 5, and 1 chloro. So it basically looks like so. Oh, sorry, I put FL. So there's 5 fluorines and 1 chloro, and then there's 2 carbons because there is an ethane in the middle. Okay, guys, so it's nearly 3 o'clock, so I think we will stop there, but do finish the questions that are in the packs because they are very relevant to what we have covered. But you guys have done really well. I know there was a lot of content today, and a lot of it was quite challenging if you have not done this before. Even if you have, they are difficult concepts to grasp. So well done. I hope to see you guys next month where we will be doing NMR and infrared spectroscopy, which is also tricky, but we will break it down. But otherwise, I hope you guys have a really good month. Take care and stay safe. I wish you all the best, and see you soon. Feel free to log off, but I will remain for the next few minutes if you guys have any questions.